Oh, okay. Okay, so let's start the conversation. So first of all, if I was calling, I'm going to tell us about the Muon demonstration of expertise. Okay.
Okay, thanks for inviting me here. The talk here is really going to be sort of a discussion of the recent results from our Run 2-3 that were published this year. And hopefully we'll convince you that the current Fermilab G-2 is on track to accomplish everything that we said we would. The other topics, I left that there in case there were other forward-looking things in the Fermilab Muon program that didn't get covered in the agenda. Having looked through the agenda, I think you guys did a pretty good job of covering the topic. So maybe I'll say a few future-looking things about our G-2, and maybe I'll have one slide on something that wasn't covered in the agenda already. This talk is too long. I'm going to skip some of the front material because we're all experts here for the most part, but I'll try to make it as coherent as I can. Okay, so just to remind you, the original goal of the Fermilab Muon G-2 experiment was to transport the container from Brookhaven that was used to hold muons in the Brookhaven experiment and reduce the overall error by a factor of 4 to around 140 parts per billion. In order to do that, we needed greater than 20 times the statistics and the muons that we store in the ring to get the statistical error down to the target of around 100 part per billion. And at the same time, we wanted to control systematics at least 100 ppb also. Just to remind you a little bit about how the experiment works, in order to extract the anomalous magnetic moment of the muon, we need to know the precession frequency of the muons in our magnetic field. We need to know the strength of the magnetic field that they're in. And then there's a few other constants, speed of light, charge to mass ratio, things like that. So that represents doing about a 3 times better job on the systematics than what was achieved at Brookhaven. So this is the Fermilab Muon campus way back in 2012 when this was already a sophisticated enough proposal to make a rendering to show what the building for G-2 might look like with Muon in the background and a new beam tunnel connecting back to the delivery, what's now called the delivery ring, which was the anti-proton source in the Tevatron era. Here you can see the anti-proton source. You can see another view of the buildings. And it really is a beautiful campus we've constructed dedicated to using these specialized muon beams and to use all this upstream accelerator infrastructure that became available after the Tevatron to manipulate those beams into the bunches we need or the slow spills we need and so on. Our first Fermilab result from 2021, just to remind you, we very excitingly confirmed the Brookhaven result. It increased the tension with the standard model white paper to 4.7 sigma. It was the most precise determination of AMU to date. And the combined experimental precision reached 350 parts per billion, which is very interesting for people like Priska and myself, because the design report, we were both on the Brookhaven experiment, the design report at Brookhaven intended to achieve 350 parts per billion to exactly that digit. That's what we got after run 1 in the combination. So we finally got where we wanted. We just have to move the ring to Fermilab to get it done. Of course, the goal at Fermilab was to go far beyond that with this factor of 4 in reduction. And just to remind you of these sort of 4 very basic, beautiful principles of the experiment that make the whole thing possible. And it's really why the experiment is so elegant. First of all, we need a polarized muon source. We get that naturally from parity violation in the pion decay. We capture the very forward-going muons from the pion decay, and therefore they all end up spin aligned, and you get a highly polarized source essentially for free, just collecting those pions. Furthermore, we run at the magic momentum, which is a gamma of 29.3, and that's because of this term in the BMT equation that scales with the electric field. We rely on the magnetic field to keep the particles radially confined. We need an electric field to keep them vertically confined, and that field itself has to have a large gradient. Unlike the magnetic field, which we work very hard to make very uniform, we need this one to have a large gradient on purpose to keep the muons oscillating. That would sink the experiment were it not for this fact that this coefficient out front, if you choose the proper gamma, you can make it the first order go to 0, and then you can know your electric fields well enough to apply the correction you need to extract AMU with the required precision. So that's the trick. Make that 0 by choosing gamma equals 29.3. The third thing that's really fascinating about the experiment is that we are an experiment that takes place in a cyclotron. If you just look at the difference frequency between the Larmor precession frequency of the muons in a magnetic field and the cyclotron frequency that they're traveling around, you can see that's proportional to G minus 2 over 2, which is the anomaly. It's the fractional difference that G varies from 2. That's what we're interested in. That's where all the new particles exist. And it's 800 times more precise than if you were trying to do this experiment at rest. So you see, we'd be far from being in the game in terms of being interesting if we were trying to do this at rest. Okay, the final interesting principle is we also don't have to work that hard to see that underlying muon polarization. We just let the muons circulate around the ring, decaying into positrons. The positrons spiral inward because there's slightly less momentum.
Just a second, but at rest,
Sure.
you would also have, if you stop it in the material, you would have various chemical shifts to the frequencies and so on.
You probably wouldn't have the field uniformity you want, though, if you're relying on
But
that.
there will be shifts, right? Depending on which material you stop it.
I don't think you can get an 800, but we can talk about it later. So let me understand your point better later. This is already a long talk. Okay, so they decay to positrons, and once again, because of parity violation, the muon decay, the highest energy ones tend to come out when the spin and the momentum are aligned. And so you can see just by drawing a cut on the energy spectrum, looking at calorimeters on the inside of the ring, we get this oscillation in the energy spectrum. And by counting, you can see them go up and down, and that goes up and down at the omega A precession frequency we're trying to determine. Okay, so there's a whole bunch of slides here that are really intended to tell you all the great things we did at Fermilab that made this experiment so much different and why it's really different than the Brookhaven experiment. We're using the same container, but even the container itself has a much more uniform magnetic field. And basically all the instrumentation, all the detectors, everything went through substantial upgrades to control the systematics. So in many ways, although it uses the same device, it actually is a new experiment. Of course, it relies on all those same physical principles I just talked about. So I'm not going to go through this in detail. We create pions at a target. We let them decay to muons. They go around the delivery ring. We inject them into our storage ring, and we end up with a much higher purity beam that operates at a much higher rep rate than was available at Brookhaven. That's important to keep the pileup systematics down. Okay, and then we do this injection in the storage ring where we put about 5,000 muons in per pulse. We do that at about 10 hertz, and we ran for about 40 months. So it's quite a long time to get the statistics we need at this point. We made all these improvements to the beam delivery. We inject this nearly pure beam. Once the beam is in the ring, we need to give it a kick to shift it over onto an orbit where the muons will store, not just crash back into the magnets we brought them through to inject. We have electrostatic quadrupoles that give us that vertical confinement I talked about. And it's the same storage ring, but I'm not going to go through the video. You guys can do it if you want, but this just shows the red is where we started when we first put the ring back together. And we somehow thought we were going to put the ring back together and it was going to come back and be just as uniform as Brookhaven had achieved. That was not the case. It was just as bad as the first time Brookhaven put it together. And so we spent a year shimming it. And one of the key things we did is we installed by hand 9,000 little metal shims to really smooth out the field everywhere in a way that wasn't achievable at Brookhaven without putting in that kind of effort. So that's another big improvement. And the field systems, we doubled the number of fixed probes that were usable to monitor the magnetic field. We need that. The way essentially this works is we monitor the field all the time with these fixed probes. We have an NMR trolley that pulls out and measures the field in this gap where the muons live, but of course it can't be in there while we're taking muon data, so this happens every 3 days or so. And then we need to do a whole absolute calibration sequence with special probes that we really understand the absolute calibration of. We made a lot of advances in those calibration probes. We used to always just rely on this one probe that was that was used for the muonium hyperfine experiments at Los Alamos. It was used in Brookhaven, and we've used it in our experiment. But now we've made some superior probes, including one with a cylindrical geometry and one that's helium-3 based, so you don't have the same self-shielding that you have with water samples. We built new segmented calorimetry that run much faster with faster waveform digitizers, and most importantly, they're segmented. So now we can get spatial separation of pileup, unlike Brookhaven. We implemented 2 sets of straw trackers that were in the vacuum. There was one that was used at Brookhaven. It was outside of the volume. It caught on fire at some point. There was a lot of trouble with it. But now we had very reliable tracker data from 2 stations throughout the entire experiment. Here you can see just how valuable those things are. This shows the basically the tracking back of positrons and shows the beam dynamics in the storage ring for the underlying muons. And understanding how the beam swims back and forth with coherent betatron oscillations, how it breathes, is very important for understanding systematic errors. So in the analysis big picture, we have to determine the frequency that the muons are processing at. We have to determine the magnetic field that they live in, and then we have to convolve that with the distribution the muons are sampling that magnetic field with. So we get this from the calorimeters, we get this from all the field devices, and we get this from the trackers. We rely on the codata for a few constants, because in the end, when we're extracting a mu, we need to know the precession frequency of the muons relative to the protons that we use in our NMR samples. You can think of our whole experiment as a giant co-magnetometer experiment where we're measuring the precession of muons versus protons. These all come out of codata. The important thing to point out is that they're a very insignificant part of our error. If you add them all up, they're all sort of less than 22 parts per billion, which is small relative to our experimental goal, as I'll remind you there. There's more to it than just that simple equation. We have to apply corrections for beam dynamics for that electric field we apply. That's the first correction. We can't make a perfectly magic momentum beam, so there's a correction required. The next one is a pitch correction. It has to do with the muons oscillating up and down and the other beam dynamics. And then we have a class of errors that can happen because if you think about the equation we're trying to fit, sine omega t plus phi, if the phase is not constant, if it suddenly requires some kind of time dependence, then that's a first order systematic error for us because it looks like a frequency shift. And so these are 3 different terms that are important to us because they can create this phase shift. And I'm going to talk about one of them in a little while. Furthermore, the field is not always constant. All these NMR devices are kind of looking at the average of the field over a long period of time. But we also have some field transients. We pulse devices when we inject beam into the ring. So we need to really understand the impact those transients have that wouldn't be addressed by the field systems without those specialized measurements. This is the result from run 1. The important thing to point out here is that our goal was to get to a systematic error, remember, of a total of, say, 100 parts per billion between the field and the omega A systematics. We got 159 ppb after the run 1 result was published back in 2001, not quite to our 100 ppb goal. And really, it came down to 2 dominant errors. One that comes from quad transients, and one comes from a phase acceptance error, which has to do with how the muon beam couples to the acceptance of the detectors. I'll come back to both of these in just a moment. If we had just made those 2 negligible, then we would have already hit the experimental goal with our first engineering run, which was pretty phenomenal because our first engineering run was pretty rough for lots of reasons that you'll see. So the important part was to address these 2 systematics, and you'll see we addressed quite a few of the other ones. The improvements come from higher statistics in our run 2-3 results that were published back in July, some changes in the running conditions, some systematic measurements and studies, and to a lesser degree, some analysis improvements. The statistics, we ended up with about 4.7 times the statistics in run 2-3 than we had in run 1, and so that allowed us to more than halve the error statistically. One big improvement is that in run 1, we had some damaged resistors on those quadrupoles, and what we need is for the beam to be injected and to be very stable in time so that the acceptance of the detectors isn't changing while we're performing our measurement. The damaged quad resistors meant that the beam sagged in the gap, and more importantly, the width of it changed during our measurement period. And that creates this phase change in sine omega t plus phi. We had to understand that. It took some time to do it, but we were able to address it. And by run 2, we had fixed those resistors, and this whole systematic error fell from 75 to 13 just for the residual beam stability after those quads were fixed. So that was a big improvement. That was the second largest error, and now it turned into negligible by run 2. Another big improvement was the Hall temperature stability. One of the advantages at Fermilab was we built a very stable Hall with a thick concrete floor so that the ring stays very stable and the magnetic field doesn't change in time. But we messed up and we didn't have enough Hall cooling. And so if you look at the magnet temperature, as the magnet temperature changes, the magnet gap opens and closes and makes an instability in the field. And so by run two, we had put thermal insulation around the magnet, which got rid of all these diurnal variations. And then by run three, we had augmented the Hall cooling to keep the overall temperature more stable. This is why the experiment went from being a beautiful piece of, bright blue machinery to looking like a giant toilet bowl, unfortunately. But it's really practical and functional to have it look like a giant toilet bowl. So, okay. Another big improvement was the kick strength. When we put on our kickers in run one, we realized, one of the advantages was we made them 3 times faster, but the new kickers weren't strong enough to really put the beam on a centered orbit. We spent 2 years on a major upgrade to get them to the strength that they needed. By doing that, we were able to shift the beam over to a better centered distribution in the storage ring. And when you are better at storing the beam in the center of the gap, it also reduces the coherent betatron oscillations, the size that the beam is sloshing back and forth. So that made a big improvement also. Those quad transients, this shows what happens when you pulse the quads, they vibrate, and the vibrating metal in the magnetic field creates its own perturbation to the magnetic field. And you can see over kind of a long time scale, these are sort of 200 ppb perturbations, so they're large compared to our systematic error. We really only care what's happening in these little gray stripes here. And so in order to address this error, we had to build a whole new system to run around and measure these quad transients, and it had to be able to do it while the quads themselves were pulsing. And so it was quite an effort, but by doing this and mapping this field perturbation, we were able to reduce this 90 ppb error to 20 ppb by the end of the run 2-3 period. This one was a subdominant error. It was only 37 ppb. I put it in here just to credit Dave Kawall, who's speaking at this conference. He really put a lot of time into building this beautiful Faraday magnetometer, and this reduced the error from transients from the kick from 37 to 13 ppb. There are a number of other sort of second order systematics that we also addressed. And you can see how the whole table came out here in run 1 versus the run 2-3 systematic. You can see many, many, many improvements, including these 2 dominant ones, most importantly. However, you can see there wasn't big improvement here. And this kind of tells you we're starting to hit the floor in what we can do in some of the systematics at this point. Okay, so our final run 2-3 uncertainties, we achieved 215 part per billion. That was about a 2.2 improvement over run 1. Similarly, we improved the systematics by, coincidentally, a factor of 2.2, which gets us to the point of our TDR goal, even exceeding the 100 ppb of our TDR goal. So already at the end of run 3, we've achieved the systematic that we've gone beyond what we wanted to even at the end of run 3, and things just get better in future runs, we think. Okay, so we unblinded that result. So we unblinded the run 2-3 result back in July. You can see unbelievable agreement. We couldn't have asked for a better, if we had put the plot on the point ourselves, we could have asked for a better place than Brookhaven, between Brookhaven and the first result. You add them all together, the world average, essentially, other than getting a small error bar, didn't change at all in its central value. And over here, there's a lot of things people plot that have to do with theory. Luckily, Tom's going to talk about those, so I'm going to move on and just talk about the future of the experiment now. So we deployed a new RF system in run 5. This was the first time in history of CERN, Brookhaven, Fermilab storage rings that such a system has been implemented. Janis Stavridsidis was responsible for this. It turns on in the first few microseconds, damps the CBO, greatly reduces the CBO amplitude. You can see before and after, many millimeters of oscillation to sort of a millimeter or 2. That in turn reduces Muon losses, which is another source of this phase shift that we can have. So overall, it just makes the experiment much better. And that will be about sort of half of our remaining analysis, or 2/3 of the statistics will be taken that way. So the data collection is now done. The experiment is over. We're aiming for publishing a final result by 2025 with an uncertainty reduced by another factor of 2. We sort of have roughly 4 times the statistics on tape already. Okay, now to talk about a few of our parasitic measurements in the last few minutes I have in terms of the future things you can expect from our experiment, starting with the Muon EDM. So the Muon EDM is a signal where the rotation, where the Muon plane of rotation rotates up out of the plane, and it does so out of phase with the G-2 precession phase. So what you really want to do is look at the pitch angle of decay positrons as they go through the trackers and look for an oscillation out of phase with the G-2 signal. The key systematics are understanding if you have a residual radial magnetic field that will mimic this signal exactly. And you need to understand tracker alignment and acceptance, which actually turns out to be a larger error because we think we have control of this. The run 1, 2, 3, all three of these years' analysis are nearing completion. They're stat error dominated, we can tell already. We're anticipating a sensitivity of about 5 times 10 to the minus 20, which is about a factor of 4 better than the Brookhaven current limit. We have at least 4 times the statistics on tape. With more improvements in the tracker efficiency, this number could be a little higher, but in the end, we expect to do about an order of magnitude better than Brookhaven. Not as good as J-PARC can do with this. Okay, so another parasitic measurement comes from our CPT and Lorentz violation test. The signal here is to look for a sidereal oscillation in omega A. Imagine there's some plane where something is passing through there's some preferred axis in the universe that causes, a Lorentz violating signal. So you can look for sidereal oscillation. You can look for differences between mu plus and mu minus for CPT. And then you can do global fits to Brookhaven and Fermilab to extract other parameters in the SME. The improvements here are the 20 times statistics with reduced systematics. We have a much longer lever arm because we ran for somewhere between 36 and 40 months. I was trying to figure out effectively how much of that time was useful, but it's somewhere in that range. And that was over 6 years compared to roughly 9 months of effective running over 3 years at Brookhaven. We're also at a different latitude than Brookhaven. So overall, we're expecting greater than 4 times improvement in all these sort of parameters. Interesting thing that was brought to our attention by Ryan Janish and Ramini here in this PRD that you can find was using the G-2 data to look for a dark matter search. You can kind of think of it as being very similar to the sidereal variation search, only now imagine coherent dark matter interactions can exert a spin torque and cause an oscillation in a mu or in the EDM signal. You can show up in either channel. It's, like I say, similar to the sidereal variation, but the period now isn't just fixed to 23 hours and 56 minutes. The period is determined by the mass of the dark matter exchange particle. So you can see the modification to the omega A we extract depends on the direction that the dark matter wind is pointing relative to the spin precession axis. And if it happened to be perfectly parallel, then you would just see this as an overall shift from the standard model value. However, to the extent that that's very unlikely, you also get a oscillation that's whose frequency depends on the mass of the dark matter. Stack plots are when we just add up all our data, and you can imagine as you do that, you wash out the signal, and so you get a much less sensitivity than if you do a time-resolved analysis to try and extract this oscillating frequency. This analysis is in progress, and it should be interesting and coming out within the next probably year or 2 years. We'll see. They're actively making progress. So here's the thing I would like everybody to help me think about a little bit. I wish I had a brilliant idea to present to you of what we will do with this G-2 storage ring next. I do not. And so the question is, what is going to become of Gordon Danby's beautiful G-2 ring? Do we suddenly have a 650-ton paperweight on our hands? Lawn ornament, maybe? I don't know. We don't know. We're kind of reaching the limit of what we can do. So let me explain to you sort of some of the main complications here. So you could say, why don't you just run with more mu plus? After all, we're sort of expecting to get maybe as low as 60 ppb in our systematics with a final stat error of 100 ppb. So if we just ran for 3 times more statistics, you could reduce the total error by another 25% by the time you add those in quadrature. But there are some pretty major complications. First of all, our doubling time is our biggest issue. To get that 3 times more, we would have to run 9 more years. We can't run in parallel with mu to E. They need all the beam while they're running, which would imply a 2030 start. And beyond that, we have some things with the experiment that are aging. Something upstream is degrading. We got 20% less flux towards the end of our last 2 runs due to, we believe, something degrading in the target. The straw trackers are developing leaks. In fact, we don't even have enough modules now to fully implement 2 full trackers. So this makes just simply turning on and running more very difficult, as you can see. So you could say, well, why don't you aim high for 20 times the statistics again with a full, but that would then mean you're making a full overhaul to beam delivery. You kind of need a 20 times higher rough rate again, or you face having to go up with more muons per bunch and more pile up. And so that would be a pretty significant upgrade to the beam delivery. Complicating that is that all the pulse devices in the experiment, the lithium lens that does the focusing of the pions off the target, The delivery ring kickers that we use to upstream and the G-2 kickers themselves are all kicking as fast as they can already. So those would all basically need to be replaced. And then another big complication is we would need another factor of 2 reduction in systematics. Many of the ones we have now are comparable, which would imply many more upgrades to get there. We could in turn and run mu-. The problem there is the pi minus production is down by about a factor of 2 because we're only impinging 8 GeV protons on our target, unlike the AGS, which had 24 GeV and therefore didn't have such a difference in the pion production rates between positive and negative charges. That means we need to run 6 years to match the mu plus. And in the end, it's unlikely that running 6 years really justifies the physics merit of just having a CPT test, because that's basically all you would get out of it at the end of the day. There have been ideas for using the ring for other experiments. We thought about trying to inject 300 MeV muons as a frozen spin demonstrator. Many people here know about the frozen spin. For our ring's 1.5 Tesla field, if we use 300 MeV, we can have the run in the frozen spin mode. But we found through some beam tests, it's very hard to deliver any flux. When I say significant, I mean so far we've got 0 for the ring. And the EDM isn't competitive in this measurement. So it's really just a demonstrator or a proof in principle. There's been proposals in the past to use the ring as a spectrometer to determine the neutrino mass, I should say. There was much work by Priscilla on this in the past, and it's just not competitive with current limits, but it's an idea. Think of it as a spectrometer, possibly with its large uniform field. Or you can imagine using the field itself for an array of detectors. We briefly explored whether there was any way to put an array of Project 8-like detectors all the way around, but the ring is just not a good geometry because you sort of have B pointing up in a 10-centimeter uniform gap, and it's not conducive to that kind of experiment. But if you have an idea for an array, then that would be great. We'd welcome any new ideas you have. Otherwise, we'll have to decide what we're going to do with this ring. The last slide I want to mention that I didn't see covered in the program yet is an idea that's been gaining some traction, and that's M-cubed at Fermilab. This is the idea of impinging approximately 15 GeV muons on a target and looking for dark matter through a missing momentum signature. I'm not going to talk about it too much because that's similar to Na64 mu, and we're going to hear much more about that later on in the workshop. But in phase 1, they would like to use 10 to the 10th muons. Phase 2 would do 10 to the 13. And you can see they can set some pretty interesting limits relative to G-2 signals, or relative to Na64. They're not competitive in phase 1, but because of the higher flux at low energy, they're competitive in phase 2. And all this is in the context of muon field forces to start with. There's a working group that's currently developing a proposal we've been encouraged by the director to do it following the SNOMAS work done for the SNOMAS LOI. And that's all I had to say. Thanks.
Thank you.
So one of the interesting cases with this Lorentz violation, if you like, is when these external fields are actually rigidly related to the geometry of the Earth, that they move together. And so you don't get the time modulation, but you would get a signal if you circulate the muons the other direction. Is this possible to actually flip, or they change the sign of the muons? Is this possible to flip the polarity of the magnetic field and circulate them the other way? Or
it would be very difficult to inject them in the other direction. It'd be quite a substantial upgrade. It's fairly trivial to run mu minus.
Okay.
It's not trivial. It's 3 or 4 months of work. And we had planned to do that a year ago and went through the whole planning exercise, and we're starting down the course of spending a long summer shutdown to convert to mu minus. But it's not compatible. It's compatible with mu to E's mu plus running that they are with the running that mu to E needs, because we have to switch polarities of devices that they need the other polarity. And so we thought about it. We could do it in the future, but post mu to E future. Yeah.
Chris, could the ring possibly be used to improve the muon lifetime measurement?
I'd have to think about it. It seems unlikely to me based on everything that was important in the Muon experiment that we don't have, like a perfectly spherical detector. It seems tricky. Do you have an idea?
You can store the muons for a very long time.
Yeah. Oh, right. No, the problem is we can't, and the reason, Priska knows the reason too. We did a measurement of relativity in the Brookhaven experiment, and we just don't have control over the lifetime coming from things like muon losses and other things that change the lifetime also to be competitive with the beautiful muon precision. Yeah, we'd have to somehow really control muon losses better and know them, as one example.
This 15 GB Muon beam, it doesn't exist yet, right? Or does it?
No, but the 10 to the 10th is imagined as kind of a minor modification for what we already do in terms of bringing beam to the test beam. And then the 10 to the 13th is a future project that requires more significant main injector flux. So, but there are plans for upgrades to have a booster replacement and potentially more 120 GB beam available beyond Dune's needs. Right now, that beam will basically be saturated by Dune and the test beam, but in a future longer term endeavor, it might have excess 120 GeV beam for something like this.
For the Lorentz violation, you say you're looking for some sort of daily modulation. Do you have any significant backgrounds that also have daily modulation as well?
No, because the sidereal period is 23 hours, 56 minutes. We would have to worry about diurnal variations, but we took data for such a long amount of time that they don't seem to be significant source of systematic. And you can just look in a periodogram and look at how the signal looks at 24 hours versus 23 hours and 56 minutes to confirm that.
I see. Basically, if you integrate for longer than a year, then you see the difference between.
Yeah, because you start getting out of phase with whatever was happening with the 24-hour clock. Yeah. These are great questions.
Okay, last one. I guess you already answered, but is there any no way to increase the beam intensity further to reduce the running time? 9 years to 1 year.
Possibly in the future, in the far future, when you're fueling the beam with PIP2 and you have a booster that runs at 20 hertz instead of 15 hertz and has able to accept more protons in the booster per bunch, possibly, but it's a pretty long-term endeavor to think about that. Yeah.
Okay, so let's just keep the rest of the discussions during coffee break. So thank you.
Thank you.
Okay, so
Okay, so the second speaker is Mibe from KK, and then he's going to tell us about Muon acceleration and Muon GMS 3DM at J-PARC. So please.
Okay, thank you very much for the invitation. And after learning these beautiful results, my talk does not have any result. So, but we are trying to make some interesting inputs to this GMS2 and EDM probe. Okay, so this is a picture of what we have at the moment at J-PARC. We have 3 experimental sites. This is for the partial installation of GMS 3DM. And this area is for muonic hyperfine splitting. And another area is muonic 1:2s spectroscopy. So those are the ongoing project. And GMS 2 is a little bit behind, but the other 2 experiments are running. Okay. Yeah, so the title of the workshop is Muons in Minneapolis. So I'd like to tell a little story about the Muons in Japan. So this is the famous ring and the famous gentleman standing in front of the ring. So this is the recently broadcasted in Japanese science documentary called Cosmic Front. And we know, so now most of the Japanese knows about this ring and this gentleman. And then
give a picture.
Okay, and then no, our experiment is also partially introduced, but thanks to this Fermilab G-2. Anyway, so just to recap the status, we have several questions in Muon G-2. The first, the standard model, there will be another talk by Tom about this. So this is a question mark in green. And what we would like to do is, okay, what if this value has some unknown systematic, perhaps it's not unlikely, but it's unlikely, but J-PARC is trying to answer. Well, if there is a question here, so J-PARC result should resolve the question. So after resolving those old questions, then we can talk about the most important question marks. And of this, if this G-2 anomaly persists, then the next step is to understand the origin of this anomaly. The Muon EDM offers the way to study the time reversal symmetry of beyond the standard model if this is the same origin. Okay, so this is the one-page summary of our G-2 experiment. So unlike the Fermilab G-2, our experiment involves the cooling section. First, we are going to stop the Muon and cool down, then put that into the linear accelerator by this to get accelerated from 25 milli-electron volt to 210 mega-electron volt. Then we shoot this into the storage. So there are several features. The most important feature is our emittance of the muon beam is about 1,000 times smaller than the conventional muon beam. So this allows us to use the very weak focusing. This is 1,000 times weak focusing than the Fermilab G-2. And also the good beam emittance allows us to inject the beam about 10 times higher efficiency. And then also our storage ring is 20 times smaller. It's very compact. It's not really a tabletop, but it's 66 centimeter diameter. So this is currently the only experiment to check the Fermilab and the Brookhaven G-2 results. And we also have an excellent sensitivity to Muon EDM, about 100 times better than the previous limit. Perhaps before the Fermilab 1 to 3 result releases. Okay. All right, so just to come back to this master equation of spin precession. So in this equation, we have a G-2 precession and the motional spin precession in motional magnetic field due to the electric field. And the third term is the EDM precession. And our approach is just turning off the electric field so that the equation becomes, the second term drops out. The equation becomes rather simple. There are two terms. The component parallel to the magnetic field is proportional to the G-2. The component perpendicular to the magnetic field is proportional to the electric dipole moment. So we'll use this to be sensitive to the both magnetic and the electric dipole moments. Okay. So the Muon beam is the major part of our improvement, and it's usually the Muon beam comes from the pion decay, and pion comes from the proton hitting the nuclear target. So the beam emittance inevitably becomes large. So this is a beam like a flash rate. So what we want to do is to implement another step of cooling and acceleration. This will make the beam like a laser beam. So the emittance becomes about 1,000 times smaller. And a few words about the EDM and the radiomagnetic field. In the case of the EDM measurement, what we measure is the spin precession component away tilted. How if the spin precession vector is tilted away from the magnetic field, then this is the EDM. However, as I explained, there are two terms, and the first term is gigantic, 10 to the fifth time larger than the EDM, the second term, EDM term at least. So if the first term includes this, the magnetic field includes the two component, axial and radial component. This radial component mixes to the second term. So this becomes a systematic uncertainties. So this. Okay, so in the case of our experiment, we are going to use a very weak magnetic focusing. So this gives us a bonus for G minus EDM measurement. The Fermilab and Brookhaven experiment uses electric weak focusing with a field index of around 0.1. We adapt very weak magnetic focusing, so no electric field. We apply a very shallow potential of magnetic field to create a focusing. So this came from the idea of Blum and Yannis Dimitridis. Our focusing strength is 10 to the minus 4th. This translates into the magnetic field gradient of 1 ppm per centimeter. Okay, so this is like a very shallow potential. So if there's a radial magnetic field, this is okay for us. This for the Muon will find a potential minimum, including this radial magnetic field, and find itself that the radial magnetic field is 0. So this is the experimental principle that our experimental method does not have any systematics associated with radial magnetic field to the leading order. And this very weak magnetic focusing is also very powerful to suppress a correction called the pitch effect. And in our case, our estimate is 10 parts per billion correction to the G-2 measurement. Okay, so this is our collaboration. We have about 10 countries, 100 members at the moment. And this is the J-PARC. This is a proton accelerator complex consisting of proton linear accelerator for 400 MeV acceleration, followed by a rapid cyclosynchrotron to get 3 GeV proton. And then we have two destinations. One is the main ring. This is to create neutrino beam for the T2K experiment, and also the slow extracted proton beam for secondary beam experiments, including the comet. And another destination is directly the beam delivered from the rapid cyclosynchrotron, where we plan to install our experiment. This is called the Materials and Life Science Experimental Facility, MLF. So our experiment has already started partially the construction from upstream. So this red arrow is a 3 GeV proton beam, and it goes through this 5% loss target, graphite target, and the produced pion and the decay muon are captured by those 4 beam channels. And we are going to use one of the beam channel called H-line, and those beamline component has already been installed like this. And about a year and a half ago, January 15th, 2022, we first delivered the beam to the beam branch. This is our beam profile, and this is the positron, decay positron measurement. From this, we estimated the beam intensity 7 times 10 to the 7 per second. So this is consistent with expectation. So in the end, we're going to have a 1 megawatt beam power and 10 to the 8th muon per second to the experimental area. Okay. Then at the moment, we are working on extending this area, having another extension to install the initial part of the G-2 experiment, namely the muon cooling part, followed by the RF acceleration cavities. Right? Initial the first 2 stages of acceleration part. So this radiation shielding has already been fabricated, and we are trying to install our apparatus one by one. So this is the schematic diagram of how our experiment works. So we start from the about the 4 MeV, so 3.4 MeV surface muon coming, and we stop those muon in a silica air gel, and when those muon stops, then it captures an electron to form an atom called muonium. And then after muonium is formed, it's electrically neutral so that they can diffuse out from this material. And when those muonium come out from the material, we shoot a laser to strip off this electron by using a ground state 1s to 2p and then 2p to unbound, or 1s to 2s and then 2s to unbound. So by this way, one can have the bare positive muon at the energy of thermal energy. This is about 30 millielectron volt. So this is 8 orders of magnitude reduction in energy. Therefore, the cooling can be realized in this process. Then after that, we electrostatically accelerate and put those muon into the conventional RF acceleration cavity. So this is the basic idea. Okay, and this is an actual picture of the silica air gel, and we tested this in a Triumph back in 2011, 2013, and 2018, and we successfully optimized our target to have enough number of muonium in vacuum. Okay, and at the moment, this year, we are working very hard to do the demonstration of ionization, laser ionization of those muonium in vacuum. So this is the actual, the experimental apparatus, and this gentleman is installing our muonium production target like this. And the laser light is shoot from the side. And we can already show some preliminary the data indicating this such a cold muon from silica air gel, ionization of muonium from silica air gel. So this is the experiment. What we do is we shoot the laser and then followed by some acceleration, 10 keV, followed by electric bending for energy filter and magnetic bending for momentum filter. Then finally we put the MCP. This is a sensor to count muon, count the muon. So there's a huge peak. This is the laser light reflected all the way to the end inside the vacuum chamber. And after a microsecond after, we have a small peak. This is the signal of our cold muon. And at the moment, we're trying to understand these numbers and characterize these emittance features of those muon source. But the good news is that we successfully observed the signal. So this is one of the progress. Then after that, we plan to plug those muon source into the RF cavity. We have already prepared the RF cavity for this. So this is the picture, the test assemble of those muon source together with RFQ. We are going to install this set perhaps the early 2024 to demonstrate the acceleration of the RF acceleration of those cold muon. Okay, and then after that, we have another accelerator components, the two accelerator components to get accelerated to 4.3 MeV acceleration. This we plan in fiscal year 2025. So this is the simulation, how our acceleration works. So we start from the vertical axis is kinetic energy. Horizontal axis is the position. So we start from 0 energy, and then we have a gradual acceleration, and then finally get accelerated to about 210 MeV kinetic energy. So this is the bottom figure is the typical RMS beam size. Our beam size is typically a millimeter, sub-millimeter size. And if we translate those into this the emittance, so this is the emittance. The top plot is the transverse emittance. This is the normalized transverse emittance. So we are well below 1 pi millimeter. So it's the unit is wrong. 1 pi millimeter in radian, and the longitudinal emittance is 0.02 or 0.03 ish. So this is the muon beam we are going to have at the end of the accelerator. Okay, so this beam allows us to inject the muon beam into this very small compact storage ring. This is our storage ring. This is 20 times smaller, and the magnetic field is about 2 times stronger. So the small storage ring is better in terms of field uniformity, so that we can only concentrate on very small volume. And this is the example of, this is the calculated average field uniformity in 25 parts per billion per line. So this has, so for comparison, I put the run one, Fermilab run one field uniformity map. Okay, so this already tells us, okay, we have smaller is better in terms of field uniformity. Okay, so inside the field, the storage ring, we install the Muon tracking chamber to detect, to reconstruct and detect the decay positron. This is allow us to have a sensitivity of EVM as well. And we are at the moment making this tracking detectors consist of silicon strip sensors. Okay, so this is here the overall schedule. So we are already start construction, and our plan is to start taking data in about 2028-ish. And towards this, we have several milestones. So first, to demonstrate the muon source and the acceleration at each stages. So those are the milestones we are going to make in coming years. Okay, so and lastly, I think Kitano-san already introduced our muon source might be useful for other application like future colliders. This is a longitudinal and transverse emittance map, and our muon source is out of this scale. So if we take advantage of these features in this the future collider planning, that would be great. But yeah, so I think for such a project, our experiment is a kind of a demonstrator for such a future steps. Okay, to summarize, we plan to measure a Muon G-2 and search for Muon EDM with a sensitivity of 1.5 times 10 to the 24th centimeter. Experiment adopt the new method the first low emittance muon beam, so using a cooling and acceleration. And we use the compact storage ring, and we use a very weak magnetic focusing. So those are the main features. Experiment is under construction. We expect the date of data taking from 2028. Thank you very much.
Thank you. So time for questions and comments.
Go back one slide.
That's
Go
right.
back one slide. Out of my curiosity, why in under Mu Tristan is that dreaming is free? What do you imply there?
Yeah, so this is not my slide. This is Kitano-san's slide. What does this mean?
I want you to feel free to dream.
Okay.
Not because it costs nothing to dream. Okay, just to make sure. Go back to the preliminary data when you try to use laser to ionize the muonium.
Yes.
Yeah,
Was it?
slide 20, the data.
20.
Yeah.
20, yeah.
So is the gap caused by the slow motion between your separation between where your muonium is and where the
Yes.
detector is?
Yes. This is a time of flight. Yeah.
I see. I see. So it's clear for us. This is your ionized muons.
Mhm.
And how many of them? Just number wise?
Right. So this is so just the very beginning. We count at that time a few muons per minute or so. So very small, very small at that moment. But we are making progress to increase these, and finally, what we want is 10 to the 6 muons per second.
And you think that's definitely achievable?
Right, right. So we know this is the laser power is very small, so that number is small. So we understand why this is small.
Thanks.
Since this is a forward-looking Muon workshop, I just want to steal Alexei Petrov's question from the Tau workshop, which you're probably very prepared to answer now, I'm sure. It seems like you're making the perfect muonium source for an MM-bar experiment. So is anybody looking at that?
Yeah, so some people are interested in using our muon source for muonium anti-muonium conversion experiment. Yes, and the idea is to just to reverse the electric field to the negative, so that converted anti-muonium, because then after ionization, negative muon is left. So the idea is to, instead of extracting positive muon, we extract negative muon. Look for the negative muon to search for conversion. So the experimental setup will be very simple, but the sensitivity and those and so forth, this has to be worked out carefully. And I think at some moment our colleague has do the back of the envelope calculation, and it is comparable to this syndrome, so previous limit in PSI. So we might need more studies or upgrade ideas to do something better.
Great. And then my other question was, how close are you now to getting that source to the flux you need for the error bar you showed earlier?
Right, right. So at the moment, I think this is almost zero, and so on the other hand, there's another area where we have much more strong laser system, and there we have about 100 muon per second. And what we want to do is 1 million. So we have 10 to the 4th larger muon is needed. So this we believe can be realized by using our intense surface muon beamline, and also the intense laser system. So combination of those two will give us another factor of 10 to the 4th. So this is going to be demonstrated in coming years.
Thanks.
Yeah, hi, Chris's question was sort of mine, but so in the end, your statistics limited, right? And
Yes.
where, if you just could have all the muons you wanted, at what point do you get down to where you're systematic limited?
Oh, yeah. So we at the moment, let's see, yes. Yeah. So our estimation of statistical uncertainty is 460. This is similar to the round one, Fermilab round one of Brookhaven, so to speak. And our estimation of systematics is 70 per variance so far. So we have this more than factor of say 6 to 7.
So one extra advantage of having muons stopped is that you can rotate their spins or flip or manipulate.
mhm.
Have you ever considered flipping the spins, rotating to sort of study more maybe systematic errors when you get to the
Yes.
to the measurement of EDMs or G-2?
So I think this in the initial discussion, initially we thought this is going to be very powerful, understanding the systematics, and Brookhaven people and Fermilab people we have consulted, and in the end we learned perhaps this is not as powerful as we thought. But nevertheless, we are going to install this spin flipping feature by changing this laser ionization time. We apply a very weak, small transverse magnetic field to rotate the spin, and ionization. We can choose the laser ionization time so that the muonium spin can be in any direction. So we can choose the orientation of the muon spin at any direction. Yes, so we are going to have that function.
So along this similar line, can you also consider repolarized muonium to recover this polarization?
Yes, we wish to consider this. There are two possibilities. One is to use a circularly polarized laser system to make this laser pumping type of repolarization. So that's one. Another possibility is to apply a longitudinal magnetic field so that electron spin is sort of locked along the direction of magnetic field. The second one sounds easier, but if we think about the extraction, then it has to go through this stray magnetic field to the field zero region. So there's another, that's a technical challenge. So we are thinking of both directions, but at the moment we have no clear.
What is the transition between hyperfine splitting?
That is well.
That is RF.
No, it's not. So if we apply a strong enough magnetic field, then the good quantum number is this Z component of the spin. So the hyperfine is no longer a good quantum number, so that one can lock the muon spin.
But then you can excite, say, one state or something.
Oh yes, so that's another third method. That will give us we can selectively ionize the muonium so that we throw away perhaps half the number, but we improve the polarization.
So the figure of merit is better.
Yes, figure of merit is better. Yes. So that might be another option.
Okay. So yeah, let's thank Mibe-san again.
Thank you very much.
I think we can have this first slide. So we will come back at 3:30. Yeah.
Rotate. So you can find like this, because like up signature down, you just rotate that.
I was actually not. Why? Yeah. What? Oh yeah, that's possible. That's much more powerful than I guess the reason you do 30 electron beam accelerating electron goes longer base. So they're fairly powerful. No, so try. Wow. Oh my God. Thanks a lot. Yeah, it's wavy out problem. We know there's a it's just it only kicks in as I just every single one of it. Yeah. So of course we talk about no, I have to go. In a certain slow down. Literally PDF, 1/3 average, right? They think 1/10 of average, typical X. Right. So I think it's accurate. So as you kind of you can compare with the Hadronic field. Oh, it's outgoing work. Yeah, all the it's a sub very subject. Both of you to finish past background. So now your Muon, they make electric, not the Hadron. That's true. So leading order, your background is still electric. So in that sense, your signal background ratio is slightly worse than electron fighter, but better than Hadron. That should be even more mature.
Production.
Right. Oh, then he's like, yeah, the 1 PV, 1 PV maybe. Yeah. It's yeah, when we miss I didn't even look at that calculator. I didn't see it. Anyway, yeah. It is. If you promise the steering community we are going to build a new class collider, I think the whole community will work for you. I'm very happy if you get it. Yeah. So it would be measuring. Everything works. How about proton mu? Hadronic magnetometry. That's okay. Yeah, at least a better option than Muon electrons. Maybe, yeah. It's actually also better than Muon. Because you can have a more energetic proton beam. Actually, it's
You understand the real life, we just don't, like, we don't even know gamma.
It's also dependent.
Yeah, I was wondering about
Existence. Yeah, facility. So long as you can circulate.
Oh.
In some places, maybe it's easier.
control systematic.
Run is to run.
One way to think about the scale.
Right, yeah. We anyway need proton drive.
Gamma.
Yeah.
That's not like it's just accelerating it out.
If you can accelerate the proton system energy, then we should start considering a proton collider, okay?
It's easier.
One PV proton. Well, I don't know, one PV is not.
PV is not enough.
Right.
We get into
Muon losses that we don't have a good handle on.
But one PV, one PV would be maybe in that. Yeah, it's actually because the PV central mass is 100 proton.
To radiate W.
That should be okay. No.
Yeah.
We don't want to just continue.
Radiating W.
Yeah, I wish we had a good use for the ring.
Intensity.
Wait, is that right? Like always.
It's electroweak process, right? So you say,
Yeah, I haven't calculated the gross section.
you're asking, what's the, compared to the new part of mass, you're asking
lab would be super.
what fraction of atom luminosity have X more than 1/30? That's basically what you're asking.
Yes.
And
They're always out.
Right. 1/30 is a significant.
You know, if we had a $20 million idea for that.
We need a higher
That was marginally interesting. I
At
think
some
the directors
point,
would
at
be
some
all over
point,
it.
we were talking.
Well,
Because you need a
I get a better.
you need a higher W.
The appearance, like you have,
Yes, I can compare them.
Oh, I do agree with you.
the muons to the ring, you have,
Yeah.
more like 1/10⁵, right? It's only a few
Yeah.
percent, so.
Right.
So,
That's right, yeah.
Well,
so you could.
You got a archive.
Yeah, you can.
And then the TV.
Yeah.
TV like a
With
nice, they have 100 GB.
So I have
a meter or 2 meter.
And then from that.
Yeah.
Material and you shouldn't have.
That's
Like,
right.
that's
Yeah.
enough to stop.
You're right.
all this.
But my mentality at that time was to compare with the ILC.
Yeah.
That's why.
Ah,
But it's true that okay, for physics wise, I think.
Yes, I understand. Yeah.
The decay is not completely trivial.
TeV proton?
Yeah.
Why?
easy.
Come on, we have 7 TeV already.
You have
It's a.
you say Japan is plan to build an LTC panel, we'll have another discussion.
Right.
Kilometer.
Yeah,
But using very modern
Yeah.
pixelated
It's old magnet is a few kilometers. If you have stronger magnet.
But still, it's but you also have a certain.
Our estimate, that is going to be,
That's the, you already have something.
That was the story.
You also wanted to.
Just, I mean, you're tracking
Right.
also comes through many plans.
But the better you can leverage existing things, the better. That's what it's. Say, oh, I already have this. But of course, once you have the like a.
so we also measuring.
Then you can argue like let's have another like a product.
Yeah.
Yes.
Right.
More we think about, then we more
Concern. I think there's some people.
learn how difficult
we
it
can
is. New lab.
Yeah, so.
Idea, my students
But that.
So I'm happy to. Actually, never, I never pay attention to the electron ion collider or every future collider. Always there's nuclear people. want to. But for this case, when we talk about this,
reionizing
mu
it
plus, mu
somehow
plus, or mu
Yeah,
plus, mu minus, actually the mu P is a composite.
without needing
Right.
laser.
So
or
then
anything like that.
we get.
Yeah, I think proton people is also happy, right?
Yeah.
Well, people talk about, I know people talk about.
Yeah.
Muon ion
You
collider.
Yeah.
touched about that signature. I would
Oh,
provide.
yes.
Yeah. This is for PDF. or
This is
whatever.
Yes.
So anti-muonism is negative muon plus positron.
Those probably exist.
So negative muon emit.
Yeah, I saw.
Basic
some
muon.
people, yeah. But they are just interested in the
Then
proton.
after that, we
Yeah,
Well,
no, not
focus
so,
on-
but now you can do Higgs.
Yeah.
You can actually do Higgs physics.
Right.
Yeah.
so we
so
the
there's no
experiment extract.
program.
Yeah, so EP program has a Higgs.
Right.
Higgs study.
Irrigation.
and
It's
your
probably
mu-
similar
mu
to-
P will be,
Yeah.
at
Probably
least
similar
the same.
to yours.
It should be better, right?
Yeah, but yeah, it would
I
be-
mean, E
yeah.
energy.
It's better and I think
That's the,
you have the novelty of muon P, right? Having
There-
muon
there-
P,
there-
everybody will appreciate.
There is the P higher end.
That's true.
muon.
And in fact, it's the same setup. I have a proton, I have a muon. I actually still do this forward part because I'm counting on low.
Rated target and
counts,
put it in front of a
Still all my
DCP.
interesting physics
like
happening here.
to-
And there's no hadronic activities. Hadronic ones are,
Then maybe.
the junks broken apart, the protons are
It's
all
worth looking
atomic.
into something like that.
So
Ah,
muon,
that's right, yeah.
so it's
I
really
see.
no hadronic.
More than happy to
I see.
provide
Very
our-
interesting.
Yeah.
Okay.
Well, maybe we should,
Yeah.
It'd really be done
I-
with your aerogel source and.
Mhm. I'll let you know.
Yeah.
But it's true, it's a different facility.
Yeah,
I think you
very
don't want to
small
argue
initial
that I have to
studies,
have
but
a
serious
collider.
Right.
You want to say
Yeah,
that
yeah,
the silly PV is
Okay.
That's what you wanted to say.
But
And of course, once you're getting it, then everything else is there obviously can be upgrade other things, right? That's building a P beam with a TeV is not true. I think. So it's trivial to technological, but money wise, it may not be.
Well, it's mu is already non-trivial.
Yeah, yeah, Muon.
You are our PVP. Actually, it can be same chart, right? Proton, so it's really the same acceleration line. You just need to bend them and let them head on.
As you within the same ring.
Same line, same linear acceleration, but I cannot make them head on. Oh.
talks, I think.
Yeah, they're all good.
Yeah.
Polly might have been a little fast.
They get
Me.
Well,
Polly?
yeah, I think it's difficult to get through in the time. So
Yeah.
there's always more material than there's time for.
Yep. He kind of flew through the degradations relative to time and why that will be important downstream. He mentioned a 20% reduction in flux.
It sounds like they don't really know. So he said something in the target, in the production target. So then you think maybe the target, like I guess it's like graphite in a sheath, with some cooling, like helium cool, something like this. And so maybe if the target broke or the target degraded in some way, they can't go in and look, 'cause it's all radioactive. So
That's right, yeah.
so maybe they have a problem with their target, which they're not clear on.
That until there's a period between runs where things are taken apart, they really don't know.
Yeah. Right.
Or simply replaced. Did it make a difference?
Yeah. I mean, presumably they make the target to be removable, one would hope.
Oh, okay, so it doesn't need to be a.
That's what they normally do, but I don't know, obviously, in their case. I think they only have like a few kilowatts on target, so it's not like a high power target. But
Yes, it's.
we had on ISIS, the Muon target, which again is fairly low power, we had a problem where they have the same piece of graphite in the beam for, maybe a couple, maybe 20 years. And the target itself was okay, but the radiation was enough to damage all of the cooling manifolds, all this cooling water.
Okay.
So then it started spraying cooling water. And when they built it, they didn't build it very well to actually be able to go in and remove things and fix things.
Yeah.
It's all radioactive, so it's all very hard to deal with.
Wow.
And so they had a real job. It took them, they went off for a few months trying to fix it. They take the old bits out, the new bits in, because they hadn't designed it very well.
And thought about that side of it. Obviously those who are building and designing have to think about it.
I think when they were building it, they probably hadn't built a target station for, I would guess. I don't know, or certainly not that sort of targets. Not even that high power, but it was high power for time, I think, target station. So again, it takes a few kilowatts of protons on the target. So to cause problems. When ISIS was built, it was the highest power machine in the world. So, you learn by making the mistakes, unfortunately. There you go.
So it's a continuous process of improvement.
Yeah, that's right.
It can't be ever thought of as a single project.
Yeah.
still, I mean.
You're gonna find out everything I know about the long distance. Well, that'll be a 5-hour talk. I don't think so.
Shall we start? Yeah. Okay. Our first speaker is Tang. Thanks. Please start.
Thank you. It's hard to believe, but this is the first time I've ever been in Minneapolis. So thank you, Maxime, for inviting me. I'm going to try to give you a brief but hopefully comprehensive status of where the theory for Muon G-2 lies today. But I'm mostly going to focus on how we're doing on the lattice, but I hope to give you an overall picture. I'll start with a brief introduction, and then I'll talk about the hadronic vacuum polarization contribution. And if I have time, I'll go on to the hadronic light by light contribution. Okay, this is, you all know, Muon has a G factor. And we're really interested in calculating the difference of that with 2 divided by 2. That's the Muon anomaly. I always like to start by showing this picture of the experiments because I think, they're just fabulous, amazing. These guys have done an incredible job for a really long time. It started at CERN and they got down to 7 parts per million. Then Brookhaven took over. They did better than an order of magnitude. And now Fermilab, as we saw in Chris's talk, is down to 0.2. And I guess they're going to go even below 0.14, maybe down to 1 per mil or per billion. Per million, sorry. And of course, there's the experiment that's going to happen at J-PARC. Okay, so let me start with the theory, the broad brush overview. We're talking about the standard model of particle physics, which means there are QED contributions to the anomaly, weak contributions, and then the QCD contributions. And of course, I'll focus on the QCD contributions because they dominate the theory area. So this is the status from the Muon G-2 theory initiative as of SNOWMAS 21, which really means 2022. And if you compare the standard, and basically, as far as the theory initiative goes, this hasn't changed since the 2020 white paper. Okay. But if you compare that result from the Muon G-2 theory initiative for the standard model value with the Fermilab run one only, then you get this 4.2 sigma deviation. But then, of course, Fermilab went on to do runs 2 and 3, and they announced their results in August. And that difference then, if you compare it to the 2020 Muon G-2 theory initiative results in a little bit more than a 5 standard deviation experiment.
Discovery.
It would be, except for a couple of things. If we compare to a lattice result that is also from 2020 by the BMW collaboration, we get a much smaller discrepancy with experiment. And then there was a recent data-driven result from the CMD3 collaboration, which came out early this year. And it is also gives a result that for the standard model contribution that's a much smaller discrepancy than that 5 sigma. So I'm going to go through now some of these things and show you, where those numbers come from and where we stand and where we're going, say in the next 6 months to a year. So let me talk about the hadronic vacuum polarization. And before I get to the lattice results, let me talk about the data-driven methodology or theory and how they get the number for the HVP contribution. So basically, we want to calculate this diagram. So a 1-loop QED integral, but a hadronic blob that's all orders in QCD, which is hard. And so you can get this from experiment, E plus E minus goes to hadrons, just by using the optical theorem for the imaginary part, and then plugging that into a dispersion relation, and you get this, the real part of this hadronic blob, then you stick it into this 1-loop QED integral, and you get the answer. This is what the data looks like. So you stick all of that data into this integral over center of mass energy, and you get the lowest order hadronic contribution to the Muon G-2. And down here you can see which channels contribute how much. So it's basically dominated by 2 pions, and then these are the errors. And then, as I said, along came CMD3 with a new result for the dominant pi plus pi minus, and they're way over here. Much different than the world average of the pi plus pi minus channel. And so this is a significant disagreement. They did really well on statistics, and so far no one's been able to identify any obvious issues with the experiment. And I think people are still looking at it very carefully, but so far, nobody really has a good idea of why the number came out over here instead of over here. The good news is that there's going to be a lot more data analyzed in the future to try to shed light on this discrepancy. So Babar and Chloe, which are sort of have long been the leads in this area, they have all sorts of data they never analyzed. And so they're going to go back and analyze that data, like, almost a factor of 10 more data. And then BESS 3 has more data, Bell 2, and so on. So there'll be more data. And people are also interested in going back to looking at the tau decay data if we can figure out how to do the isospin corrections.
On the plot, what's the significance of the green color on the plot? Is that like
I don't know because I didn't make the slide, but I mean, presumably it's because this is CMD3 and it was their talk. And then Chloe and Babar are the 2 most precise results before that.
On the actual figure, there's some green. I wonder if it's
it must be statistical, systematic.
The CMD disagree with it themselves.
They disagree with themselves too. That's right. Okay, so now let me turn to the lattice results and let me give you the high-level summary, which really hasn't changed since the 2020 white paper, maybe a little bit after that because BMW wasn't included in the 2020 white paper. And then I'll go through and tell you what we've been doing since then. Okay, so I want to compare the lattice to the data-driven result for the HVP. The green band is basically what the HVP would have to give you if there would be no new physics. So it would agree with the Fermilab result. And the data-driven numbers are over here off to the left, and the lattice is up here. So everybody but the BMW has errors at this point that were too big to distinguish either between the green line or the red points over here. But BMW has errors that are sub% on the same order as the data-driven error. So this is what was in the 2020 white paper. And if you compare those two things, they disagree by about 2 sigma. But that's enough for BMW to more or less be consistent with no new physics, and data-driven to be not consistent with no new physics. So this is basically where we stand for the total contribution. But now what I want to go through is tell you what we've been doing since then to try and understand more, say, carefully and quantitatively what the lattice results are and what they mean.
Other people were interrupting, so I'm going to take that. So I have been told that the BMW errors are grossly underestimated because they don't include errors for the technique. In fact, I can tell you who told me that.
You won't tell me?
I will in a second.
Okay, I don't think that's, I mean, I don't agree with that, but.
So throwing up, so can you tell us why the BMW error seems to be so much smaller than the others? When they are not much smarter, or?
Well,
Christoph.
Let's do him first.
Christoph told me. Christoph Lander told me that.
Okay, I mean, you know, for those of you who don't know, Christoph is my good collaborator.
So you said it.
No. First of all, I think the BMW result is solid. I don't think there's any serious issue with it. I mean, it doesn't mean that it's right, but I think it's as solid as, I think it's a solid result.
What's the solid result that is not right?
It's solidly not right.
Well, they tried the best they can.
I think they did a good job estimating their systematics and of course their statistical errors. And we'll have to see when more lattice results come around and we can actually compare. And then then we won't have to say what we think, we'll say what we know.
Well, does that error bar include the systematics that their error?
All of these errors have systematics and statistics.
I think the BMW error is entirely systematic.
Right. Well, BMW error is dominated by systematics. That's true.
So if they did a solid work, their result cannot be otherwise, right? Because they already include the
systematics. All I'm saying is that no one's been able to point at a BMW and say, "Oh, you did this wrong." You underestimated this error. You underestimated that error.
Bertrand's question was, why are they so much better? It was just computing power,
Okay,
right?
so I mean that's a good question. BMW, they're one of the premier lattice groups in the world. They're very good. They have a lot of people, and they have a lot of computer resources. Now, I would say they were a little bit aggressive. Maybe like all good scientists, they wanted to come out with a result, and they did. And then the rest of the lattice community, they had a choice. What are they going to do? Everybody going to go their own way and try to come out with their own number and compare to BMW, or something else? And we decided as a community to do something else, and that's what I'm going to tell you about. And but the idea, of course, is that eventually we're all going to get to the same spot. Okay, so before I quite get there, let me just tell you a little bit about how we do the lattice calculation. So it's supposed to be the same thing, so it looks a lot like the data-driven approach. But what we're really talking about now are quarks and gluons, and we want to calculate these diagrams on the lattice. Okay, so we have what we call a quark connected diagram with a hadronic blob, a quark disconnected, so it's only connected by gluons, And then similar diagrams, but where we add an extra photon for isospin breaking effects, which we have to actually calculate if we want to compare to the data-driven results, because that stuff is in their result. So, again, the idea is we just calculate the hadronic tensor from two electromagnetic currents, and we extract the hadronic vacuum polarization. We plug that into this one loop QED integral. So it looks very similar to what I just showed you for the data-driven result. And we get a value for the lowest order contribution, hadronic contribution. Now, it turns out that the community has gone on to a slightly different way of doing the calculation. It's called the time momentum representation, where we simply interchange the order of the Fourier transform on the previous slide and the loop integral over Q squared. And so in the end, what it amounts to is a calculation in Euclidean time of the Euclidean correlation function of the two electromagnetic currents, separated in Euclidean time, and then we just sum overall Euclidean time. Okay, it's the same, it's just, like I said, just flipping the order of the two integrals. But this turns out to be more useful for a lattice calculation, because after all, that's what we do. We work in Euclidean spacetime on the lattice. So here's an example of how that goes. This is that integrand that I just mentioned for a lattice calculation, the blue dots, and they're compared to the R ratio data. I think this was from Fred Yanger later's determination of R ratio, the same quantity, but using E plus E minus data. And you can see that they agree very well. They don't agree quite so well at very small distance, or where we're working at a finite lattice spacing, so you expect there to be discretization errors. So we haven't taken the continuum limit yet. And then in the long distance, it's also hard to do the lattice calculation, because the correlation function is dominated by very light pion states, and they fluctuate wildly in our Monte Carlo calculations. Okay, so I see I'm way behind. Anyway, we have to do this calculation, and we do it on several lattices with different spacings and different volumes, and then we extrapolate to the continuum limit and the infinite volume limit. And that's basically what BMW and everybody else is doing. Okay, so what did we decide to do as a community? We decided to break up the problem into 3 parts by simply breaking up the total contribution into 3 what we call windows: a short distance piece, an intermediate distance piece, and a long distance piece. And really the reason to do that is because these first 2, the short distance and especially the intermediate window piece, are already easy to calculate on the lattice, because there's not a lot of discretization effects and there's not a lot of finite volume effects, and the statistics are okay. Whereas the long distance piece is much harder, and the long distance piece is about half the contribution, and the short and the intermediate are about half the contribution. But as you'll see, we already find a significant discrepancy with the data-driven approach just for the intermediate window. And that already amounts to a big difference, most of, or at least half of the difference between the data-driven approach and the BMW result. Okay, so these are a few details. In fact, it was this intermediate window where we first saw there was maybe a discrepancy between lattice calculations and the data-driven approach. These are 3 lattice data points. If you extrapolate to the continuum limit, it seems to be systematically high compared to this open square down here, which is the dispersive result, the data-driven result for that same quantity. But it wasn't clear at this point that it wasn't just statistics or maybe some systematics. But after a lot of effort, yeah.
What's the difference between the red and the black? Sorry.
So these are 2 different lattice calculations. This was one using so-called domain wall fermions, and these are using staggered fermions. And they extrapolate, this one extrapolated to a value that's consistent with the R ratio. As we'll see in a minute, that's because there wasn't another point over here, and this thing actually does this, not this. But they're just two different discretizations, and they should also agree in the continuum limit. And after a lot of work by many different groups around the world, in fact, they do all agree in the continuum limit for this so-called intermediate window. And they're much different than you get from the R ratio, the data-driven approach. And this discrepancy, so what I'm showing here is just that light quark connected, so the up and down quark contribution, and the light quark connected contribution. And that amounts to about 1/3 of the total. But you see already that the discrepancy here is, 6 or 7 times 10 to the minus 10, which is sort of half the discrepancy between BMW and the data-driven results already, before we even get to the long distance or the short distance window.
It's like sigma, it's the second discovery.
That difference, I said it was 6 or 7 times 10 to the minus 10, but it's also 5 or 6 sigma discrepant. And so that's a really, I would say, strong consensus by the lattice community that this is the lattice value, and it's quite in disagreement with the dispersive.
You guys are all blind from each other because chi-square for that is like way too good.
We are well. So let's see. These last two results were completely blinded. The other results were not blinded. Okay, the short distance window, lattice and the dispersive data-driven approach are consistent, but the short distance window doesn't contribute all that much to the total anyway. So if there, now the thing that we have to do is go on and do the long distance window. So I'm going to tell you in the time I guess I have left, which is 5 minutes, what my collaboration, the RBC collaboration, is doing to calculate the long distance window, which is, like I said, half the total contribution. Once we calculate this, then we'll have a number that we can compare to BMW and the data-driven result. So we have these ensembles with these lattice spacings and these pion masses times L. Basically, you want M pi L to be 4, or is sort of the rule of thumb in the lattice community, 4 or greater. These are all at physical pion masses, and so the size of the lattice boxes are around 5 Fermi or 6 or 7 Fermi. And we have 3 different lattice spacings, and at this one lattice spacing, we have 4 different volumes that we're going to use to estimate the finite volume effect. Okay, so the key point here to calculate this difficult long distance contribution to the correlation function, which is dominated by 2 pion states, is to basically reconstruct the correlation function in terms of its lowest energy states. Okay, so on the lattice, all the states are finite volume, discrete finite volume states. And so there's a whole tower of them, but the more massive they are, the less they contribute at long distance. So if we can compute enough states accurately enough, we can reconstruct that long distance tail in a way that's more efficient than just calculating the original correlation function of the 2 electromagnetic currents. And what I'm showing here is on one of our finest lattice is the 8 lowest states, the energy values for those 8 states. You're supposed to go from small times to larger times and see that there's a nice plateau. And you can see that we can resolve very well 8 of the lowest states. So that's the the exponential here. We also need the coefficients, which we can also calculate in the same calculation, and these are the coefficients. Again, they all have a nice plateau, and so we can reconstruct the correlation function. And here, again, this analysis is all blinded. But what I'm showing here is the ratio of the reconstructed correlation function to the the real correlation function, or the 2-point electromagnetic correlation function, versus Euclidean time, the separation between the two currents. And you can see, of course, at small times we don't do very well because there's lots of states down here that we don't get. But at larger times, where all those really heavy states are exponentially suppressed, we start to saturate the correlation function. So we want to hit this line. And, after, so this is 1 state, 2 states, 3 states, 4, 5, 6, 7, 8. 6, 7, 8 are all up here. And the errors here are coming from the denominator, not from the reconstructed correlation function. So if you look at the integrand now, the yellow dots here, the yellow points, are the original correlation function. And you can see the noise in the long distance region. That'll kill you. But the blue points are the reconstructed correlation function. Much, much more accurate statistically. And if you use, so the idea, of course, at very short distance, you can't use the reconstructed correlator. And at long distance, you don't want to use the total correlator because it's too noisy. But in the middle, there's a nice sweet spot. There's a plateau where your errors are minimized. And so that's the key idea for the long distance correlator. And here's the results for 3 of the lattice spacings that we have. So the only thing left to do here is take a continuum limit. This scale is sort of meaningless because there's a blinding factor in here. So we don't really know what the long distance contribution is. This is just to say that, these are the results without doing any corrections for finite volume or mass retunings, say, to get to the exact pion mass, 135 MeV, and the kaon mass 497 MeV, and so on. When you do those corrections, you get the red points, and now the object will be to extrapolate these to the continuum limit, which we haven't done yet. Okay, so once that gets done, then we have some other things to do. We have to recalculate or do better on the QED and the isospin breaking corrections. Those will be in progress. And then we have more systematics to address, more calculations to address systematics like continuum limit and charm quark effects and so on. But the goal is to get to the level of the BMW, hopefully better, in 2024. And hopefully in the first half of 2024, not the second half. But we'll have to see. Okay, so did I run out of time? Okay, let me go to my, so basically the upshot is the hadronic light by light is a much smaller contribution, and it's in good shape between lattice and data driven. We can do a little better, but let me just go to my summary. So I showed you there's a strong consensus on the lattice for this intermediate window value. So the important thing to know is that no matter what happens with the long distance part, the short distance lattice and data driven do not agree. So that's something that we have to figure out why. Okay. And that discrepancy is already a large part of the original, BMW data-driven discrepancy. The short distance window is compatible with the R ratio. Groups are now working on, these other contributions, which are small, but, we have to do a bit better job ultimately. And also several groups are working on the long distance contribution. Okay, we don't know what's going on with CMD3. I just said light by light is in good shape. Good job by Chris and his collaborators. They're 2 per mil and they're going to 1 per mil. And, our goal, both data driven and lattice, is to get the same level for the theory. hopefully by the time that those guys announce their final result. Thank you.
Any questions?
Just before the hadronic light by light part. Just before the hadronic light by light part, I think you skipped a slide or two. Was there anything interesting on those or not?
No, you got the gist of it. I mean, there's one new calculation that we did for the total that appeared after the BMW. But we ended up with an error that's about 2%. So, it's still consistent with both data-driven and BMW.
But there were a few lattice groups that started to put points on the long distance window plot. Has been.
I don't think anybody's done that, at least unblinded.
No, it's. I'm sure they weren't blinded, but my question was whether BMW has put their point on there yet or not.
We asked them to do that, and they haven't done that yet.
Okay, thanks.
Perhaps there are other observables that are morally kind of connected to this correlator of the electromagnetic currents, such as, for example, electromagnetic width of phi or omega and so on, which is like omega gamma star mixing and so on. Is this possible to calculate to like a % precision and show that you can reproduce the measured values?
Maybe, so there are a lot of groups, both data-driven and lattice, thinking about ways to compare different bits of the correlation function between the two. So the one we have right now is this intermediate window. That's the one that works really well. Of course, when we get the long distance window to, sub % accuracy, we can also compare that between lattice and R ratio. You can also think of playing different games where you try to isolate some energy regime and then compare what you would get on the lattice. I mean, so there's all sorts of ideas, but I don't know that anything has been suggested that's just more effective than just, the calculations we're doing right now. Now, I mean, if you're trying to decide who's right and who's wrong or where the difference lies, then we probably have to do more than just, compare.
This would not be comparing to between themselves so much, but to a measured value, right? So like.
Right. I mean, I guess what I would say is that the idea is we want to know why lattice and data-driven don't agree. And so, somehow by dissecting each of those calculations in various little bits and pieces, we hope to understand where someone, where they diverge.
Of course, a lot of people are now interested in the tau also, since it's traditionally been over in the space closer to where BMW lives now. And there's a conference, another workshop going on right now where you can see people trying to resurrect that data and taking a look at it. It's clear it still differs spectrally a lot from the E plus E minus if you want yet another 4 or 5 sigma anomaly to work on. But my question to you is, can we get the isospin corrections for the tau data from the lattice?
Yeah. And we're working on that. I mean, there's a subgroup of our collaboration. So from the same, basically the same calculation that we do for the, isospin breaking corrections here, you rearrange it just a little bit and you get the isospin breaking corrections for tau. So that's something we're really working on.
Excellent. That's great.
So leaving the tau aside, if I look at all the data-driven points, they're not that discrepant with each other, right? It's fine. Okay, even including the Chloe-Bavar distinction.
I mean,
look at the error
quite
bars.
true.
I wouldn't.
So if you compare Bavar and Chloe, in 2 pi in the 2 pi channel, they differ by about 10 in units of 10 to the minus 10.
Yeah, but look at the sigmas. If you count sigmas, like that wouldn't.
They certainly differ by several sigma.
Right, but you expect that when you start to take a lot of points. I mean, if I saw that for a collection of data, I would not be like, oh my God, there's a problem here. So the underlying question though is, are people starting to wonder, like, is there some common problem in the data-driven approaches that might be driving this? Are people looking at that?
That's well, it's hard for me to answer since I'm not in the data-driven game, but the problem is most of the data-driven stuff was done many years ago, and everybody moved on, and there's nobody to go back and really re-examine what was going on. And like I said, the good thing is apparently now they're decided they because of the CMD3 results, they need to go back and analyze data that they never analyzed. So hopefully when they do that, that's this kind of thing will. I think if there's one issue that people are thinking about or maybe worried about, although no one's really been able to say this is really a problem or a significant problem, are the radiative corrections that they do. And that would be something that, could affect everybody.
Yeah, the Monte Carlo seems to have gotten better on that front. And so if everybody else that used the same Monte Carlo and some magnetic corrections were not that one model, then I could have affected a lot of people.
Okay, thanks.
Okay.
I think that window thing, that the intermediate window result, lattice result is only for the connected diagram.
This light core connected diagram is the easiest thing we can calculate on the lattice, and it's also by far the largest contribution to the whole thing. So that's why we focus on it. But this over here is the total. So this has all core contributions, QED, disconnected diagrams, everything, and it's still discrepant.
Yeah, I wanted to ask, the data-driven part, can you separate the disconnected and connected?
So you can, but I don't think you can do it, you have to make some choices.
Okay, so that data point is full window part. I mean, including all the diagrams for the data-driven part.
Sorry, this one includes everything. Everything on this plot is just for light core connected. But in order to get light core connected from the data-driven side, you have to make some sort of, isospin decomposition, and they claim they do a very conservative separation. I don't think it's, there's some subjectiveness to deciding what's isospin 0 and what's isospin 1. But they claim it's very conservative and it doesn't really affect, they've estimated the error in there.
Okay, let's thank Tang. Our next is a remote talk. So. Hello, Dave. Can you hear us?
Hi there. Yeah. Let's see if this is going to work. And let's go full screen.
Hello. Hello.
Hi there.
Yeah, it's good.
It's good?
It's good. Yeah.
Okay, great. Yeah, so I really wish I could have been there. The plan was to get there, and then I had a bunch of things just stack up, and it had to kind of back out at the last minute. Yeah, it's really wish I could be there. It's a great topic. So today I thought, there are many things to talk about, but one I thought I would address is magnetometry for precision muon physics. And yeah, so just thinking ahead, although of course we're in the midst of wrapping up G-2, and there are many other efforts ongoing. I think it's interesting to think about, how in the future, how are we going to do, say, 10 times better on Muon G-2 or on the Muon mass or on the Muon magnetic moment? Yeah, like what's the future of our field? So if we consider the case of Fermilab G-2, which Chris told you about, there are some measurements we have to make. We measure the Muon, pointer here. We measure the Muon anomalous precession frequency, and we measure the magnetic field in the storage ring, and from that we extract Muon G-2. And and ignoring things like the electric field correction and the pitch correction, it's a pretty simple relationship. So we hope, Fermilab maybe will get a mu to something of order 130 parts per billion, but of that, at least 50 parts per billion is going to come from the B field measurement. So in the future, if we want to do all of this stuff, say 10 times better, we're going to need significant improvements in magnetometry. Okay, and so ideally, we want to be able to do things at the few ppb level. And of course, it's going to take more than just magnetometry. The entire experiment design will have to be different. But we should start thinking about the techniques we're going to need to do magnetometry much better than we can do currently. And so excluding G-2, there's also, of course, muonium, which we'll hear about. And here there's many reasons to study muonium. One of them is that the ground state hyperfine interval is a very good way to test, bound state QED, and there are experts in the audience, of course, know tons about this. And here, it's also interesting because the size of the hyperfine interval in muonium depends on the electron-muon mass ratio. Okay, so the hyperfine splitting, normally you think about it as, it's like a spin-spin interaction between the muon and the electron times the, the delta function where their wave functions overlap. And so it gives you something like 4.4 gigahertz. And you can re-express that in a way that as a sort of Fermi term and then some higher order terms. So one approach that's been taken to these measurements is that you can measure delta nu, and then from that, you can solve this equation here for ME over MU. Okay, so you can get a very, very precise result for the mass ratio of the electron of the muon. In fact, this is the way to get it to about 22 parts per billion, but it is dependent on the theory, right? You have to know these higher order terms. So the ground state in muonium, it's described in a magnetic field, described by the Bright-Rabi Hamiltonian. So there are 4 magnetic substates, and you can write the energy levels of those. This is solved a long, long time ago. And you can basically write the energy of the states in terms of the magnetic moments of the particles. And then this dimensionless factor X, which is really just a measurement of the ratio of the Zeeman splittings over the hyperfine ground state hyperfine interval. So you can identify a couple of transitions between these magnetic sublevels, like between the F equals 1, MF equals 1, and the F equals 1, MF equals 0 state. And then another one between F equals 1, MF equals -1, and the 0, 0 state. And at very high fields, these intervals, or the splittings between these states, is basically the hyperfine interval divided by 2, and then just the magnetic moment interaction of the muon in the external field. So in very, very high field, these nu1,2 and nu3,4, they just look like muon spin flip transitions. So here's the Bright-Rabi diagram. So here, horizontal axis is the B field. On the top, it's in kilogauss, and in the bottom, it's in this dimensionless factor X, and here are the splittings. And so you can see it up here at very, very high fields. You can think of this nu1,2 splitting as a muon spin flip, and the nu3,4 is another muon spin flip. And so you can see here roughly what these these frequencies correspond to. And if you add them together, the sum of them is equal to the hyperfine interval. And the difference between them is basically a measurement of the muon mass, or sorry, the muon magnetic moment. So the takeaway here is, okay, if you want to extract delta nu, so the ground state hyperfine splitting, all you need is actually the relative value of B. Okay, you just want to measure nu1,2 and nu3,4, and you just want to make sure that the B values are comparable. You don't need an absolute value of B, because when you add these two together, the actual value of B cancels out. So you just want to do the experiment such that the B values are the same. It doesn't matter what the actual value is. So for the ground state hyperfine splitting, you just need a relative value of B when you're measuring these transitions. On the other hand, if you want to get the muon magnetic moment out of this, you have to measure the two transitions, and then you have to measure B, because then you can get the muon magnetic moment. Okay, so in this case, then you would need the absolute value of B in order to extract the muon magnetic moment. Okay, so how do you make absolute measurements of magnetic field? So the basic idea here is like, so here would be, say, our muon in some external field, and we want to measure, we typically in all of these experiments, we measure some kind of precession frequency of the muon, and we want to know the local B field. So the simplest thing we could do perhaps would be to put a proton in there, a free proton, and then it would precess in the B field with a frequency which is given by the gyromagnetic ratio, which is known to extraordinarily high precision now due to recent results in these double penning traps. The gyromagnetic ratio of the proton is known to 0.42 parts per billion. So in principle, you could do absolute B field measurements to sub ppb if you could measure the precession frequency of a free proton, because you just take this divided by the known gyromagnetic ratio, and you can get B. So this would be extraordinary, but of course it's impractical, right? It's very hard to deal with free protons. Okay. Similarly for electrons, the gyromagnetic ratio of an electron is known also to extraordinary precision, but it's impractical for use as a magnetometer. Okay, so what are our other options? Well, the neutron, it's of course, continuing this line of completely impractical things. Its magnetic or its gyromagnetic ratio is not known that well. It's 240 parts per billion. So it's impractical and is not very good as a magnetometer. So there are a couple of options that people use. Typically, one of them, which is now becoming more common, is to use the helium-3 atom. Okay, so we call this shielded helium-3 because you typically, as your magnetometer, you use an atom, but the thing that's sensing the field is the nucleus. And so the nucleus is shielded by the electrons. So the precession frequency is going to be modified from that of the free nucleon because of the diamagnetic shielding of the electrons. So the precession frequency of the nucleus, helium-3 nucleus in a helium atom would depend on the gyromagnetic ratio of the shielded atom. Okay, and that's known to roughly 12 ppb. There's actually a new measurement I'll talk about in a second, which is much more precise. And the other thing, this is what we've used a lot in G-2. Of course, we also have a helium-3 measurement in G-2, which I'll talk about. But we've relied mostly on the shielded proton in water. So it's the same idea. You put protons in water, so the gyromagnetic ratio of a proton in water, so that's indicated by this gamma p prime, it's different than the free proton by about 25 parts per million, but it is determined pretty well, right? So you can do absolute magnetometry with protons in water in principle at the 10.5 ppb level, okay, if you take care of a bunch of details. Okay. So this is the advantage that it's practical to do this stuff, and it's reasonably precise. Okay, so how would you make a probe? Okay, so here's our proton in the water molecule. Ideally, what we want to measure is the precession frequency of a proton shielded in water. Okay, but that's not going to be identical to what we measure with our NMR probe. Okay. So some of the ways it would differ are that, okay, this shielding I told you about, the fact that the protons in the water molecule are shielded by the electrons, that shielding is actually temperature dependent. Okay, so the gyromagnetic ratio of protons in water is actually temperature dependent. So you have to correct for that. The other thing is that, you can't just do the experiment, or maybe you could, but it'd be awfully hard, with a single water molecule. So typically you have a macroscopic sample of water. And the complication there is that, you may have your NMR coil or whatever surrounding some finite part of the volume, but the rest of the volume of water is magnetized. And so the magnetization of the water over here makes a B field over here where your coil is. Okay, so the shape of the water sample matters. Okay. So that's this additional term here. So that this epsilon here is a shape factor, which in the case of a sphere is 4 pi over 3 in CGS units. And so the shape of the water times its magnetic susceptibility perturbs the field value that you're measuring, perturbs the precession frequency. So you can see ideally, okay, let's make a spherical probe where epsilon is equal to 4 pi over 3, and that would cancel this term. In practice, that's difficult. I'll tell you about that in a second. So what we've been doing is to use cylinders where epsilon is equal to 2/3, and you can make very precise cylinders. So the uncertainty on this epsilon term is pretty small. But then the consequence of that, so this factor turns out to be, so 2 pi minus 4 pi over 3 times the susceptibility of water. This term in here constitutes something like a 1.5 ppm shift. So, you take what our probe measures, but in order to interpret it as a magnetic field, you actually have to shift the value by about 1.5 ppm. That's a pretty big shift compared, when you want to measure fields at the ppb level. Okay. So as I said, ideally we'd want to make spherical samples, but it's pretty hard to do that. The other kind of amazing thing is that the value of the susceptibility of water, that's the best known value, actually comes from a measurement in 1933. And there's a story to tell there. I'll tell you. Anyway, so there are other complications too. The fact is, you can't just have a sample of water as your NMR probe. You also have, you have to have an RF coil. The water has to be in some kind of container. You've got to have some kind of cable, maybe a bit of electronics and so on. So all of these other materials perturb the field at the site of the protons. Okay, so the field of the proton over here actually is affected by the magnetization of all of these materials around. And so you have to know what this effect is. So the magnetization of probe materials further perturbs the field at the site of the protons. So in G-2, we've worked very hard on these factors and measuring these things and knowing what they are. And so we know most of the factors in these brackets here to about 15 parts per billion accuracy. But looking ahead, that's not going to be good enough. Like we really want to get all of this stuff down to the few ppb level. So this is what one of our absolute calibration probes looks like. This is an image, and this is in reality what it looks like. And it looks like nothing, and that's by design. It's really designed to perturb the field in a minimal way. So you try to put all of the electronics and everything else far away from the water sample and far away from the NMR coil to reduce all of the perturbations. And with these, it's a pretty simple design, but when the conditions are good in one of our MRI magnets, you can get, here I show a set of measurements where, the range of, the resolution of the probe is at the 100 parts per trillion level, or even better. It's mostly driven by the drift in the field. So you can measure stuff, easily, sub ppb trivially with these probes. And the problem is converting what these measurements are to an absolute magnetic field. So by taking care of all of the corrections. So just some of the things that complicate these measurements. One is that this RF coil here, that's the closest sort of asymmetric thing to the water sample. And so it's a source of field perturbation. It's also asymmetric. And also any currents in this coil. So of course, the coil is sensitive to these precession spins. You end up with currents in these coils, and those currents cause magnetic fields, which in fact perturb the field seen by the protons. So these radiation damping currents actually perturb the field. So you have to design your probe to minimize those effects. So looking ahead, ways we could improve on these probes are this: we use a so-called zero susceptibility wire. So it's a wire made with a combination of aluminum and copper, because those guys have opposite sign magnetic susceptibilities. So ideally they would cancel, but they don't completely. So there's a residual effect due to the magnetization of the RF coil. We tried a long time ago an idea of replacing these commercial wires with copper and aluminum foils, where you can adjust the width of these foils to precisely cancel the susceptibility. And it actually uses less material, which is fine, because in these RF systems, all the current flows on the surface. So you don't actually want a wire. A foil is better because you get lower resistance and smaller amount of material. So we pursued this for a bit, but we were kind of running out of time to optimize it. But in the future, this would be the way to go. You can use less material, so you have a smaller field perturbation. You can precisely match the width of the foils to completely eliminate the susceptibility. It has a larger surface area, so you have a smaller resistance. And yeah, so there are ways to improve these coil designs. The other thing is our probe is made with an aluminum shell. And what you can do is combine aluminum with Teflon. These again have opposite signs of susceptibility. So that would make these material effects go, as close to zero as we could get. So that term on the other side, the material effect, could go to zero by combining materials with opposite sign susceptibility. We can further, make the probe better by making the components lighter weight and farther away from the active volume over here. The other thing that actually, by design, it wasn't a problem for us, was this issue of this radiation damping. So the currents in these coils, any person working in NMR who would look at this probe would think we're crazy because we put our coil so far from the sample. But it's by design, because we wanted to minimize the effect of these currents in the coil on the field seen by the protons. And so you have to minimize the so-called filling factor to reduce the shift in the precession frequency caused by this stuff. So in any case, yeah, I think, with control over these things, we should be able to reduce, like, we know how our probes behave maybe at the 15 parts per billion level. We should be able to get that down significantly. We can measure corrections in an MRI magnet at the few ppb level. And I think there are ways to reduce these other sources of complication down to a few ppb level. So I think in principle, there should be a way forward. So the other thing, let's step back now. Let's imagine here is the equation that we really like, where you measure the precession frequency of a free proton, and there's the gyromagnetic ratio of the proton, which is known extremely well. But we can't do that, but we can interpret the measurement of a probe in a spherical sample of water. It's related to a free proton by the diamagnetic shielding. So this is so the precession frequency of a proton in water is related to that of a free proton by diamagnetic shielding. So currently that's known to about 10 ppb. I'll talk about that in a second. So in principle, we could do better by improving this measurement of the diamagnetic shielding below 10 ppb, or maybe get that down to a few ppb. The other approach, of course, is, okay, let's get rid of that problem and use a different atom or molecule for which the diamagnetic shielding is known much better. Okay, and that's a lot of the motivation for doing it in helium-3, because in helium-3, you can actually calculate the diamagnetic shielding, because it's not a complicated water molecule. I mean, it's still complicated. I could never do it, but the theorists can calculate this diamagnetic shielding. And as I talked about, okay, we can minimize this term here by careful design and careful choice of materials. The other thing ideally we'd like to do is to use a spherical sample of water. And that way we would eliminate this term on the susceptibility of water. The problem here is that to get a few parts per billion uncertainty on this term here, you need sphericities to a few tens of microns on centimeter scale objects. So if your water sample is a few centimeters or a centimeter or so, this thing has to be spherical to 10 microns, and it's just a challenge. Okay? So that's why we've gone to cylinders, because it's much easier to do that. But ultimately, if we can get a spherical sample, this term basically goes to 0 instead of being something like 1.5 ppm. So as I mentioned, another thing we're doing in G-2 is to make a helium-3 probe. So this is work this is driven by Tim Chupp's group at Michigan. And the idea here was, okay, so here, if you do NMR with water, the precession frequency of a shielded proton in water depends on the magnetic moment of a free proton modified by this diamagnetic shielding. In the case of helium-3, it's the same sort of expression, where this would be the magnetic moment of the nucleus, and then this is the diamagnetic shielding, caused by the electrons. So just looking at the values of some of these factors, so the diamagnetic shielding of water, this was measured in Bill Phillips. This is not precisely what he did, but you can interpret what he did in terms of the diamagnetic shielding of water. It's known to about 11 ppb. There is a measurement by Neronov and Surerigan, where they measured the diamagnetic shielding of water to about 2.5 parts per billion, but it's not being incorporated into the co-data measurements because they feel that the systematics were not maybe addressed properly. It's a pity, because this would be fantastic, because this would have, if the whatever, if the concerns could be addressed, because then this would enable, absolute magnetometry at a few ppb level using water probes. So looking at the helium side of things, the advantage of helium is that this diamagnetic shielding, although it's twice as big, more than twice as big as in water, it can be calculated. Okay, so it's basically perfectly known, due to the amazing abilities of the theorists. So that's the advantage of helium-3. This term is can be calculated. So there are measurements where people compared, you put a water probe and a helium probe in the same field, and you can measure their relative precession frequencies. And this is being done to 4.3 parts per billion. This is really nice, because in principle, this is a kind of benchmark. And the reason you want to use these two different kinds of probes is they have very, very different systematic uncertainties. So for instance, in helium, there's no uncertainty from this term, basically. So for G-2, we want to tie our water probes and helium-3 probe together and see if, the way if we put them in the same field at basically the same time, we want to see that the frequencies they measure are consistent with the measurements of the ratios of these magnetic moments. Now there's a new measurement of the helium-3 moment. It differs a little bit from previous ones. So this just came out last year. This is a direct measurement of the helium-3. Okay, it's the ion magnetic moment. And it's an absolute measurement of the magnetic moment. That's this result here. This is a result where they just compared the relative measurement of water and helium-3. So there's a bit of a discrepancy here. As far as, say, interpreting G-2, I wouldn't worry about it because it's a 20 ppb uncertainty. So however this gets resolved, it doesn't mean that there's something fundamentally wrong in magnetometry. If there is, this would only say it's something at the 10, 15 ppb level. It's not something we would need to worry about at this stage anyway. But at Argonne, and this is a lot of the work of David Aguilar at Michigan, we're comparing our water probes and the helium probes, so we can independently check this kind of relationship. And we would hope to do these comparisons at the 10 ppb level Because if we can get consistency between water and helium-3, it's kind of a bulletproof check of the magnetometry for G-2. So just to go back, this is the kind of final part of the story. This term here, I told you that currently we use cylindrical samples, so this epsilon, I'm sorry, I'm switching between CGS and SI units. This is an SI units. For a cylinder, epsilon is a half. So, so this term is 1/6 times the susceptibility of water. This is something like a 1500 ppb correction we have to make to every measurement. Okay. And there's a kind of crazy story here. Okay. So everything depends on this susceptibility of water. And if you go back to CODATA from 2000, there's this write-up about, what is the best value to use for Chi. And so they, Peter Moore and Barry Taylor said, well, this is the value they get. And it's based on this paper from Auer in 1933, corrected to 22 degrees C using the mass susceptibility measurement of temperature data of Philo and Fairbank from 1980, converted to a volume susceptibility using mass density data versus temperature from Patterson and Morris, and corrected the result of Auer for the accepted difference between the international ampere, which he used, and the SI ampere. So there's a ton of conversions between data taken in 1933 and all of the changes in fundamental constants, not fundamental constants, but in standards of measurement in the interim. So one kind of amusing thing is that okay, Taylor and Moore, they had to correct Auer's data using mass susceptibility data of Philo and Fairbank. But if you look in Philo and Fairbank's paper, what they actually measured was volume susceptibility, and then they converted it to mass. So like these two guys are canceling each other. And they're both, they're all using different standards of density and temperature data. And so it's kind of a crazy, it's really a very complicated business. But the bottom line, everybody agrees, is that the absolute value for the susceptibility of water is very poorly known. Some of the other things that have gone on since Auer's measurement, there've been changes in the temperature scale, many changes. There's some uncertainty in the water isotopic composition and density, which depends on the way that the water is prepared, like how it's distilled. I told you about how, some of the measurements are made with magnetic or mass susceptibility and not volume susceptibility, and they differ by the density of water. That in turn depends on what people use as the cc or the milliliter, and they in fact changed over time. So the whole business, the milliliter was used back in the, the milliliter was not the same as a cc in older times. Anyway, so there's a story here. There's a lot of complications in what's the best value for the susceptibility of water, the volume susceptibility. Here's this, the best measurement comes from this Auer in 1933. And the idea here was you look at the distortion of a water meniscus from magnetic forces. And he did this amazing job and got basically the most precise measurement. There have been other more recent measurements. Blott and Daniel did one with a squid magnetometer in 1933. This was their result here in SI units. It differs from, or it's basically consistent with ours, but we don't know the temperature at which Blott took his data. And these values are discrepant with other data from Day and Picard and others. And Schenk wrote a review paper, and this was his value for the susceptibility of water. This value here is different from this value here, and this value here is different from this value here. So there's a great deal of uncertainty. Anyway, so there's probably not a real problem, but it does seem like a lot is based on a 1933 measurement. There are a lot of corrections to go from the 1933 measurement to get to a current value because of all of these changes I talked about, the changes in temperature scale, changes in definition of cc, milliliters, change in the ampere, changes in the measurements of the density of water and so on. Other things that our measured, like a temperature dependence, is different than what Philo and Fairbank measured. So there's reason to be a little bit concerned about this value. If you take two of the values you get for susceptibility of water at 20 degrees C, and you put them into the expression for cylindrical samples, it's a 4 ppb difference, but I don't have a lot of confidence in that it's just 4 ppb. And when we're talking about fundamental physics, people will question everything if we find a result different from the standard model. So it would be better to have better control over the susceptibility value. And looking ahead again, having a better value is required if we want progress in magnetometry and precision muon physics. So we have to do better on this guy if we're going to use water. Okay, so we are pursuing a new measurement of this, and we're just exploiting the fact that term I showed you, how the frequency shift depends on the fact that you're using a cylinder of water, but in fact, it depends on the angle of the cylinder with respect to the magnetic field. And so if you compare when the cylinders is parallel to the magnetic field or perpendicular, and if you can measure that difference precisely, you can get a very good value for the susceptibility of water. It's basically a 4,500 ppb effect. And so the value of chi depends on how well we can measure this difference. So our colleague at KEK, Kenichi Sasaki, is working on a measurement where we're doing exactly what I just talked about, putting a cylindrical sample of water at different values or different angles with respect to a magnetic field. You measure the frequency shift. Turns out the effect of air, so the fact that the sample is displacing air, is hugely important. So we have to do this because air is paramagnetic, because of the oxygen is paramagnetic, making air paramagnetic.
Sorry to interrupt. Could you wrap up perhaps?
Yep. Oh, sorry. Yep. This is the last slide, in fact. So this technique looks promising. Right. So, right. My perspective here in the spirit of a workshop is to look ahead to next generation of experiments. So if we're going to do 10 times better in muonium, or a new G-2 experiment or something, we're going to have to improve absolute magnetic field measurements down to the few ppb level. Of course, we'll need many other major changes in experiment design to make B field measurements at this, so the B field measurement of the overall experiments at the few ppb level. And so, for instance, next generation Muon G-2 experiment, probably we would want a magnet that has no iron, that's persistent mode, and just purely superconducting. Anyway, yeah, sorry for going over. That's all I have.
Thanks, Dave. Questions?
Sorry, Dave, Chris here. Why did you say no iron? I didn't quite follow why.
Well, as you know, an iron, like, an MRI magnet has no iron in it. So something more like that. Something kind of looked like a Helmholtz coil in some, actually pairs of Helmholtz coils.
Thanks.
Just because, as you know, the iron moves around, it's just not stable, and because the field you get depends on the gap, and you can just never get the gap between the iron poles, at the ppb level. At the below a ppm level. It's just impossible. So I think a next generation experiment would probably just want a pure superconducting magnet.
Okay. Let's thank Dave again. Our next speaker is Ting. Okay. Hello. Okay. Okay, thanks everyone for coming here. My talk will be based on a recent work with Yohei and Maxim on the Muon spin force, which is a BSM scenario, which, if it exists, would possibly explain the G-2 anomaly. I will first review the Muon spin dynamics, where we will see why we care about a force that acts on the Muon spin, and where this force could possibly come from. Then we will see how this force could be constrained, either indirectly from nuclear spin force experiments, or possibly directly detected. Then I will end with some brief comments about how the same idea of indirect constraints could be used to put constraints on the Muon EDI. Okay. In the Muon's raster frame, the precision frequency of the Muon is very easy to write. But as we have already seen in a few talks before, when we go to storage rings and boost the equation to a relativistic frame, as well as accounting for the direction of the motion of the Muon, things gets more complicated. In storage rings, the second term here goes away because the velocity of the Muon is roughly perpendicular to the magnetic field. For the third term, the Brookhaven and the Fermilab experiments choose the gamma value 29.3 to cancel it, and J-PARC choose to eliminate the electric field. But as we can see, even if we only consider the force from electromagnetism, it is non-trivial to simply read the Muon G-2 from the precision frequency. If there is a new force which interacts with the spin and change the precision frequency, then it would completely change the story. One possible such interaction is an interaction between the Muon spin and a special direction. It would modify the Muon spin dynamics both in the raster frame and in storage rings. Then if this type of force exists and we don't know it a priori, then when we observe the Muon G-2, it would appear to us that this observed value is shifted by a value which is proportional to the Muon spin force. And if its value is the one given here, which is 6 times 10 to the negative 14 eV, then it would produce the same effect as the observed G-2 anomaly we currently have. So let us discuss where this force could possibly come from. One possibility is to have a lattice scalar field, which has scalar coupling with the nucleons, and as an axial vector of pseudo-scalar coupling with the Muon. And here we normalize these two types of couplings in this way, so that when we calculate the tree level effect, these two are equivalent to each other. But as we will see later, when we include the loops, they still have different effect. In the non-relativistic limit, this interaction becomes an interaction between the muon spin and the direction from the nucleus to the direction from the nucleon to the muon. This type of interaction is small for individual nuclear muon pair, but if the scalar field mass is small, then this interaction could be concurrently enhanced by the large number of nucleons in the entire Earth to produce an observable effect, which could possibly be observed in storage rings. This idea has been discussed by several authors before, and the goal of our work is to see how nuclear experiments can constrain such type of effect. In order to do that, let us first discuss how the same type of interaction, but with nucleus instead of muons, are done to constrain the nuclear spin force. This will both give us some numbers for setting indirect constraints for the muon spin force, as well as telling us some idea about how possibly we can directly constrain the muon spin force. Those nuclear experiments are typically done with isotopes. In this particular experiment, they use the isotope xenon-129 and xenon-131. They fill these two isotopes in the cold magnetometer cell. Then the cell is put in a uniform magnetic field generated by the coils. Then there are magnetic shield to screen the outside magnetic field. And finally, the whole thing is put on the rotation table and the tilt tables so that they are able to adjust the direction of the magnetic field. Then in such experiments, we can measure the ratio of the precession frequency between those two isotopes. And then by reversing the direction of the magnetic field, we will get another ratio for the precession frequency. In the absence of the nuclear spin force, these two ratios would be equal to each other. However, if there is a spin force, then these two ratios will be different. And calculating the difference will give us some idea about the size of the spin force interaction. To see what we can observe from such experiments, let us define the interaction in the form given here, where the first one is the Euromagnetic dipole interaction, and the second term is the spin force interaction. Then we can calculate the ratio of the precession frequencies. For the xenon isotopes, the result is given here. There are also terms from the rotation of the Earth, which we can eliminate. So, which we can eliminate to a very good accuracy. From this equation, we can see if the spin force and the G factor are proportional to each other among isotopes, then there is no sensitivity. Otherwise, some effect can be detected. The current best limits are done for the mercury isotope by University of Washington, and for the xenon isotope by USTC. their values are given here. If we compare those values with the one required to explain the G-2 anomaly for the Muon, then these nuclear experiments are many orders of magnitude back. So this could possibly allow us to afford a loop transfer and consider the spin force transfer from the muon to the nucleus. At the lowest order, this can happen through a muon loop and 2 photons. The photons can be either on shell, which gives us some one loop effect, or they can be off shell photon, in which case we get an interaction between the scalar field and some fermions. And as we will see later, here the pseudo-scalar and axial vector coupling starts to be different. At a one loop level, the axial vector coupling is suppressed by the factor here, as well as the numerical factor 1/12. Then, in order to estimate the size of the effect, we need to know the magnetic field and the electric potential distribution inside the nucleus. The electric potential distribution is easy to get, since nuclear charge can be well approximated by uniform charge distribution. However, it is difficult to estimate the size of the magnetic field because we currently do not have reliable nuclear model to explain the nuclear magnetic dipole moment. We use a model where the magnetic field comes from the valence neutron and co-polarization of the entire nucleus. Then the valence neutron contribution is obtained by numerically solving the Schrodinger equation in Woods-Saxon potential, and the co-polarization is modeled by a uniform polarization, which reproduces the correct magnetic moment. Doing this model, we got the loop transfer factors here. And when combined with nuclear experiment limits, we get the constraints for those 2 types of muon spin force. Comparing with the required value for G-2 anomaly, you can see the pseudo-scalar coupling is ruled out by a few orders of magnitude, but the constraint for the axial vector coupling is uncertain due to nuclear uncertainty. In particular, the one for the xenon isotope in the axial vector coupling case comes from numerical cancellation of the 2 effects at a 1% level. And we definitely do not expect our nuclear model to have such a good accuracy. And then we move on to look at the 2-loop effect. We are different from the 1-loop case, where the pseudo-scalar coupling dominates. Here, the pseudo-scalar coupling is suppressed, and the axial vector coupling plays a more important role. After computing the 2-loop effect, we got the loop transfer from the muon to the quark length. Then we can use lattice to speed models and nuclear spin expectation values to translate the axial vector coupling with quarks to the one with the nucleus. Then we get the loop transfer factor here. And when we combine with the experimental limit, we get the constraint on the muon spin force here. This is kind of stronger than the one required for the G-2 experiment. But this result could be undermined by the nuclear uncertainty at one loop. On the other hand, the constraint from the mercury isotope has better one loop behavior, but their spin content are poorly known, and that prevents us from deriving a two-loop constraint on that. So the constraint for the axial vector coupling is uncertain. To address this uncertainty, we think about possible ways for directly detecting the muon spin force. In order to do this, let us go back to the precession frequency of the muon in the presence of both the magnetic field and the muon spin force. We can see in order to distinguish these two effects, we need a way to adjust the size of these two terms. And this is easiest if we can have the ability to change the size of the magnetic field. And it would be even better if there is a possibility to reverse the direction of it. And we can also see the size of the muon spin force is larger for small gamma. So it is easier to detect it with stopped muons. Then the size of the muon spin force for G-2 is equivalent to a very small magnetic field at 1.1 milligauss. So it might be easier to detect it if we have a relatively small size of the magnetic field. So is all these requirements possible to achieve? There is an experiment which was done half a century ago using similar setup. Their goal was to detect to measure the magnetic moment of the mu plus. And the accuracy they achieve is about 2 orders of magnitude weaker than our requirement. So given the experimental progress over the last half century, it would be completely possible to use similar setup to detect the muon spin force or exclude it during stopped muons. In order to do that, we see the precession angle caused by the muon spin force during the muon's lifetime is a small number, which means we need a large number of muons. But this is not a problem given the number of muons we can deliver per second. Then we need a uniform vertical magnetic field in the range 5 to 50 Gauss, with the possibility of reversing the direction, which is possible given that the experiment done before us had a magnetic field around 66 Gauss. Then we want to use co-magnetometer to precisely keep track of the magnetic field. And then the muons can be stopped by either liquid or gaseous targets. And then the size of the muon spin force can be extracted by looking at the change of the ratio between the precession frequency of the muon and the co-magnetometer as the muon, as the magnetic field changes. Okay, finally, let us discuss briefly mention how similar idea of loop transfer can be used to put indirect constraints on the Muon EDM. The idea is the Muon EDM can generate the electron EDM and the CP out light by light operator through loops. And then those operators would contribute to the major class of EDM observables, which are the paramagnetic EDM and the dimagnetic EDM. Then using the current experimental limits on those two classes of EDMs. For the paramagnetic EDM case, we were able to derive a bond given here, which is a factor of 20 better than previous Brookhaven measurement. And for the shift moment, which comes from the dimagnetic EDM case. We were able to use the constraint on shift moment for the Milky Way atom to derive a constraint on the Muon EDM, which is a factor of 3 better than BNL measurement. So to summarize, the existence of a Muon spin force could explain the G-2 anomaly if it has the size shown here. And then the Muon spin force can be indirectly constrained by nuclear spin experiments. The constraint strongly rules out the pseudo-scalar type of Muon spin force, but it's uncertain for the axial vector spin force due to significant nuclear uncertainty. The Muon spin force can also be directly detected by using Muon spin resonance experiments using stopped muons. And the same idea of loop transfer improves the Muon EDM bonds by a factor of 20. That's all I want to say. Thank you for your attention.
Questions? So on page 30, you estimated this translation to delta E xenon using, yeah, here. It's what are these models? What did you do?
Okay, so we first calculate the loop transfer from the the axial vector coupling between the scalar field and the muon to axial vector coupling between the scalar and the quarks. Then we get the effective Lagrangian here. Then from the quarks, we use the lattice 2CD model on the axial charge to translate it to the axial vector coupling with the nucleons. And then we use nuclear models on the nucleon spin expectation values to interpret the axial vector coupling with the nucleus. Then we were able to use the experiments on the nuclear spin force to constrain the Muon spin force.
Yes. So in this last step, you did some nuclear physics. What exactly did you do?
Sorry.
It's some other groups who did the nuclear physics,
okay.
so we just borrowed it.
And why is there a log of m tau or MP appearing?
There are just some the IR and the UV scale we choose. This is relatively conservative. We just choose the IR scale to be the 2CD scale, which is MP, and choose the UV scale to be a conservative one at M top.
Okay.
If it's a tau minus mu symmetry, then the
the UV part of the law cancels above and
But there's no tau. I don't know. It was just mu.
but this is a free parameter, right?
The couplings to tau is a free.
Yes.
Yes, that's true, but still.
Well, we want to derive a conservative limit, right? So we therefore one could choose a you know, like a reasonable coupling that minimizes the model.
Okay, I don't know. All right.
It's just a numerical choice for logging UV over IR.
So slide 16, you talk about MuSR. So you have data from whatever 1950 or whatever.
Yeah.
But there's loads of data on MuSR since then. So is there no better value? I mean, there's an industry in MuSR, right? But there's no better data on.
This is mainly because they use some situation which is similar to what we expect. They use a relatively weak magnetic field, and they use stopped mu.
Most of the MuSR is just condensed matter explorations of the local magnetic field, right? Here you want like as uniform a magnetic field without any variations due to the matter, so to speak, and then measure very precisely the magnetic moment of the mu to well, it's doable, of course.
So you'll forgive a couple of dumb experimenter questions. You said, you don't have to go back to slide 7, but you were talking about reversing the direction of the magnetic field. So if Chris ran the muons in the opposite direction, would you get a different number?
Sorry.
So there's a counterclockwise, if you ran this same experiment in the same place and counterclockwise instead of counterclockwise, I'm looking at your slide 7, would you expect that he'd get a split?
This.
Chris, so in the G-2 experiment.
Okay.
Yeah. I'm thinking for the same reason as that last bullet. If he ran clockwise versus counterclockwise, you get an opposite sign effect.
Yeah, that would be complicated. Because first, if we use the same type of particle, like mu plus, both for the clockwise and the counterclockwise direction, then they would then reversing the direction of the magnetic field will make the mu plus move in different directions, which requires injecting the muon beam in different directions.
Okay.
And that would be complicated.
Okay.
Chris already said that it's easier to inject mu minus than to.
No, but I was just trying to understand.
Yeah, sure.
Yeah.
Yeah.
The second thing, so this I remember that when at some point people talked about limits on axions from supernova explosions, coupling to muons from cooling.
Yes.
Does that have any effect on your model?
Yes, that would also put a constraint on this type of coupling. But
must have been thinking about the other thing.
But their bond could be relaxed when the muon also has a scalar interaction with phi. So we want to explore other possibilities to constrain this type of coupling.
Okay, thanks.
Maybe I missed it, but have you considered fifth force bounds from like torsion balances and equivalence principle tests?
But microscope is this. Right?
Microscope. Okay, I see it. Okay, thank you.
Supersedes everything now.
Okay.
For the long range.
Oh yeah, now I see it. Okay, sorry, missed it. Thanks.
Yeah. Okay. Let's same thing again.
So that is at the end of the day 1. So enjoy Minneapolis and let's
measure the susceptibility of beer or something. Which is will be very recent measurement.
Set an indirect EDM limit on it. I would suggest you use your indirect limit for better limits on any other fundamental particles.
Yeah, we
Like
have
how-
done
how-
charm, bottom,
charm
core